I kind of want to sing another REM. No, I want to sing Ahead by a Century. That's by the Tragically Hip. Ah, here it is. Good, good, good. All right, here we go. First thing we climb a tree, and maybe then we talk, or sit silently and listen to our thoughts. Illusions of someday, cast in a golden light. No dress rehearsal, this is our life. And that's where the hornet stung me, and I had a feverish dream with revenge and doubt. Tonight we smoke them out. You are ahead by a century. You are ahead by a century. You are ahead by a century. Stare in the morning shroud, and then the day began. I tilted your cloud, you tilted my hand. Rain falls in real time, and rain fell through the night. No dress rehearsal, this is our life. Well, that's when the hornet stung me, and I had a serious dream with revenge and doubt. Tonight we smoke them out. You are ahead by a century. 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 And disappointing you is getting me down. Hydrate or drive, absolutely. That is good. Dihydrogen oxide. That is very, very good. Dihydrogen oxide.
Okay. Alright. My mic on? I think my mic is on. Yeah, when the squirrels start running in circles and then the crows start crowing, that means it's time to get this thing going, right? Let's see if I got it set up here. Oh, yeah, we don't have a video yet. Okay, I think we're there. Almost. Oops, there we are. Yep. All right. I've got some. I found these little. I don't have any headphones yet. Good ones anyway that I could wear on stream. And I found these little speakers that are essentially headphones and speakers. There's no amp in this or anything. You just plug it in, and it's wired directly to the speaker. So it's basically headphones in a speaker. So this I think this will work a little bit better for me in terms of trying to monitor my stream. So hi, this is Double Tribble, and it's Double Tribble stream on August 9th, and it's 5:17. So I started about 7 minutes later, or 10 minutes later or something. So sorry about that. I was in the shower and didn't realize it was getting that close to 5 o'clock. I think I set this for 5 o'clock. Anyway, I think I got the right title on there this time. I'm gonna attempt a live experiment, at least one live experiment, maybe more, and talk about Plancks Constant and yeah, radiation, that kind of stuff. For those of you who are aware of what Plancks Constant is, you know what I'm talking about. Those who don't, you learn something, and I'll learn something, because there's this part of Planck, a lot of parts of Planck's constant that I don't understand. So maybe we'll learn something. So I put live learn in there because I'm going to try to learn about this live on the air. So all right, so I'm going to attempt an experiment at some point, but I stream a lot of different stuff. Let me just, at the beginning of this thing, for people who are watching the VOD, this is a live stream. It's real scuff, you know. I've only been streaming a couple weeks, so it's not like a YouTube video where somebody has edited it down to 20 minutes or 10 minutes or something, and everything's rapid fire. This is going to be be just speaking off the cuff, live. No edits, no cuts, nothing. It's just I'm just talking. I got a little camera here. That's part of my experiment, maybe. I don't know. I don't know if it's going to work or not. And so I stream a lot of different stuff. Tonight I'm streaming science, and I want to try to stream a lot of science and technology. And we got a mic still. I don't know how loud this is. It's saying that I'm putting out a lot here of mic, but I'm not used to this speaker, so what I'm gonna do is okay, I got that maxed out, I think. I'm gonna lurk in on somebody else's stream here. Okay, mine is not loud enough. I can tell that right now. So now, oh, I see what the problem is. Okay. All right, I think we got it now. All right, that's usable, I guess. I'll try not to vary the, maybe you can turn it up a little bit or something on your end, and I'll try to close mic it as much as possible and try not to vary the audio too much. As I said, I'm still learning this stuff, so I made a little checklist, because this is really complicated. For me it is anyway. It's really complicated. You got all these settings all in different places, so I tried to make a little list of all the stuff I had to do. And I think I got it. I got the title up there right. I've got, hopefully you can hear me. I've got video. I didn't adjust the webcam, but that doesn't look too bad, right? That looks pretty good for what we're working with there. So I wanted to talk about Planck's constant and blackbody radiation, and it's there's a lot of stuff that goes with it that kind of like prerequisite information that you need to understand before you get to Planck's constant. A lot of stuff. So I don't know if I'm going to be able to cover it, and if I'm going to be able to cover it cleanly. I didn't really practice this. Normally when somebody explains something or teaches something, they think about it a little bit, how they're going to present it in the beginning. I didn't do that, so I'm just going to speak off the cuff from what I know, and maybe find some YouTube videos that might be useful. I'm not really sure where we're going to go from here. But Planck's constant, I'll go through the whole, it's a little bit of history. He came up with Planck's constant around the turn of the 20th century, like the 1900, somewhere around that time. And what the scientists were trying to explain or understand was that, when you heat something up, like if you've ever heat like a flame, right? That's something that's really hot and it makes light. And anything that you get hot enough will make light. If you take a piece of metal, put it under a flame for a long time, it'll start glowing red, and if you get it really, really hot, it'll glow white. And what that is that's called blackbody radiation, and specifically blackbody radiation in the visible spectrum that we can see. The electromagnetic spectrum is like radio waves and X-rays. It's all kinds of stuff. Microwaves, visible light. That's all in the electromagnetic spectrum. And it turns out that everything in the universe radiates electromagnetic radiation all the time. And that's called blackbody radiation. And we may not be able to see it. Most cases we can't see it, but it's there. It's radiation. So your own body, my little water here, everything, this microphone, everything you see, everything you don't see, everything in the universe radiates electromagnetic radiation. And the reason that it radiates is because of a fundamental principle of electromagnetism. There are 4 forces that we know of, maybe fewer, maybe more, we're not sure yet. But right now there are 4 fundamental, they call them interactions now rather than forces, because, anyway, I won't go into that. So there's one of those, there's gravity, there's some, the strong force and the weak force, and electromagnetic force. And electromagnetic force is responsible for just about everything you see except for gravity. All the interactions. The reason why when you touch 2 things together, they don't. You can't pass your finger through it, right? It stops. I can't. When I push my finger in my hand, it doesn't just go through. And when you think about it, when you actually look at what your finger in your hand is composed of, it's composed of tiny, tiny, tiny little bits of matter. They call them particles. They're not really particles. They're waves. They're matter waves, standing wave. And when you look at it, it's mostly space. It's just a tiny bit of it is these little waves, but the rest of it is all space, open space. Almost like if you look at our solar system or the universe or anything, it's all space, and there are tiny little things in there. And if you took like 2 solar systems and pushed them through, tried to push them through each other, they would just go right through each other. Or 2 galaxies. That happens, in fact. When galaxies come together, they just go right through each other. But matter doesn't, for some reason. And the reason it doesn't is because of the electromagnetic force. The electrons, the way electromagnetic force works and charges work, there's a plus charge and a minus charge. Electrons are minus, protons are positive, and there are other more exotic particles. I'm going to call them particles too, because it's just we're all used to that. It's not really particles. There are no particles. Okay, it's all waves. But like charges repel each other. So if you get two electrons coming towards each other, they're going to try to push each other apart. And two protons coming towards each other will push each other apart. But if a proton comes to an electron, it'll get captured, or can get captured, and they will attract each other because one's positive and one's negative. That's how charges work in the electromagnetic force, electromagnetic interaction. So that's why you can't push your finger through your hand, is because when it's all open space in here. It's all just a lot of space with these tiny little wave functions, or matter waves we call particles. But most of it's space, so you should be able to push your hand right through, but it doesn't because of the electromagnetic force. Because in all the atoms in the molecules that make up your hand and your finger are composed of protons, a nucleus, which is a proton, at least one proton, and usually neutrons, and electrons that are near it, an electron cloud, they call it. Because it's not like you've seen these pictures where they show a little ball in the middle, that's the nucleus, and a little ball on the outside that goes around. That's not it. It's a wave. It's all waves. So anyway, the molecules, the atoms and molecules have electrons around them. So when something comes close to those atoms or molecules, it's going to be mostly negative. You can have polar molecules and stuff like that, like water, but they'll push away from each other, and that's what causes that. When you go to push like that, the electrons in my finger on the outside of my finger atoms, and the electrons on the outside of my hand atoms push against each other. That's why I can't push my finger through my hand, or push through any matter very easily. So what was I saying? So all those electrons and all those molecules, those atoms and those molecules are always moving. They're always moving all the time. And that's thermal energy. We talked about this on the last science stream I did. We talked about thermal. I tried to explain how to convert from Celsius to Fahrenheit for folks in the U.S. who are confused by Celsius. But anyway, everything is in motion. They've tried experiments, and they've done everything they can to try to get down to 0 Kelvin, and they get 0.000 Kelvin or whatever. I don't know what the smallest number they've gotten to so far, but there's always some motion there, and it turns out that a charged particle, either, for example, an electron or a proton or whatever, a particle that has a charge, when its vector changes, that means, like if it's moving, if something causes it to change its speed or its direction, that's changing its vector. In physics, they refer to that as an acceleration, even though it may decelerate by the common term. It's still an acceleration. It's a negative acceleration, they call it. But it's changing its vector. So if it speeds up, slows down, changes direction, does anything, that's a change in the vector. And it turns out that anytime a charge particle or charge carrier, it could be a whole, it could be an ion, could be an entire atom, anything that has a charge on it, when it changes its vector, it emits electromagnetic radiation. And the more the faster, the more the change is, the more particles that do that, and the more the more the change in vector, the more energy in the electromagnetic wave that goes out. So when you take a piece of metal, for example, and you heat it up, all the molecules and all the atoms and all that get moving really, really, really fast, and they're bouncing into each other. And every time they bounce into each other and change in direction, they emit an electromagnetic wave. And when they move fast enough, they can emit waves that are in the visible spectrum, and that's why we see the red glow or white glow of the metal. So if there's a property of light that it turns out that the more the shorter the wavelength, you know how waves work, right? I don't think I need to explain waves, right? Waves, you got a wave that goes like this, right? And it has a function of time and movement and all this. But if you have a wave that goes up and down really fast, then the wavelength, the length between the start and the end of the wave is going to be shorter, right? Higher frequency means shorter wavelength. And it turns out that the shorter the wavelength is a function of the energy of the photon. This is what they discovered. That Planck and then Einstein kind of worked it out, and it's there's a direct correlation between the wavelength of the electromagnetic radiation and the amount of energy it has. And the reason that is because the energy comes in packets, and that's what we call photons. The photons, again, aren't particles; they're waves. Everybody talks about the wave particle duality or whatever. You know, it's all waves. You know, don't get confused about that. There are no particles. Everything is wave. So a photon, if you put more energy, if a photon has more energy, it's going to be a shorter wavelength, or inversely, a higher frequency, right? And the lower frequency electromagnetic waves, in other words, the photons with lower energy and longer wavelength, are things like radio waves and heat and that kind of thing. Then when it gets up to, and then it gets higher and higher, it gets, you have different types of radio waves. Everything below infrared they call radio waves. So you get up to higher and higher frequencies of radio waves, and then you get into microwaves, and then it gets into infrared, and that's what like we emit. Have you ever seen these little cameras, these infrared cameras that can detect the far infrared? The terms on infrared, they have terms. They call it near infrared or far infrared, and that just means how short the wavelength is, and how close. The near and far means how close it is to visible light. So like just ordinary stuff, people and matter and things like that, rocks or whatever, anything you take a picture with this infrared camera is going to be far infrared or mid infrared. I don't know what they, but it's further away. It's a longer wavelength than near infrared, like an infrared LED. Some of the cheaper cameras can do infrared, but you have to light up the subject with an infrared light. But they're the true infrared cameras can just take pictures of, you know, a landscape or something and get a picture just from the energy that those things, that matter, is emitting. So near infrared means it's close to visible light. Far infrared means it's far away from infrared light. Far infrared, you got to have a real expensive camera or more expensive camera that can just take pictures of the objects that you're looking at, just on the light, the infrared that those objects are emitting naturally. And the cheaper cameras, you know, like these little cameras with little LED lights on them and stuff like that, will the little infrared LEDs will light up the subject. They'll send out near infrared electromagnetic radiation or infrared light, and it'll bounce off the subject and come back into the lens of the camera. And it's a lot easier to design a camera that will detect near infrared than far infrared. Far infrared's a lot more difficult to do because you got, among other things, you've got the infrared that the camera itself is emitting, right? If everything emits infrared, even the matter that the camera is made out of is emitting infrared. So that complicates things. That's infrared, and heat is in an area too. And then once you get into above infrared, then it gets into the visible spectrum, and the lowest end, which is the longest wavelength or highest or longest wavelength or lowest frequency light, is red. You got infrared, and then as soon as it gets to the point where where human eye can see it, they call it visible light, and it's red. And then you see all the colors in the rainbow, right? It goes in red. I don't forget the order, but it goes all the way up. Red, orange. What is it? Green, yellow, blue. You know, all these different colors, and then violet. And then once you get up there, violet has a short wavelength compared to red. In red, it's about 700 and something, I think. I forget what the numbers are, but it's about 700 nanometers. Nanometer is really small, a billionth of a meter. Take a meter, and then millimeter. Millimeter is pretty small, right? You can still see it, but it's pretty small. And you go to micrometer, which is a thousandth of that. So you get a meter, which is, I don't know, from my nose to the tip of my hand maybe. Then you cut that by 1,000, you get a millimeter, which you can still see with your eye. Then you get down to micron, or a micrometer, which is a millionth of a meter or a thousandth of a millimeter. You need a microscope to see that. And then you take 1,000th of that, even, and then you get to a nanometer. So it's really small. So, and it's, we're talking about wavelengths, right? So it's moving really fast, right? Because light goes at a constant speed, so it has to be moving really fast. So on the low end of the visible spectrum, it's around 700 something, or maybe 6. I forget what it is. 680 maybe. And that's red. And then on the high end is blue and violet, which is that's about 700 nanometer, and then on the high end it's around 400 or so nanometer, which is shorter. Right, 700 is a little bit longer. 400 is shorter wavelength, and that's the higher frequency blue and violet. So the frequency is moving really fast. It's short wavelength, and it's all measured in nanometers in the visible range. And then when you go above that, then they call it ultraviolet, and they have different conventions that they use. Right after when you first get out of the visible spectrum and get into ultraviolet, around, over smaller than 400 nanometers. It gets smaller, it gets 390, 380, like that. Then that's they call it near ultraviolet or ultraviolet A. That's a type of, when you buy black light, black light that you get for makes thin glows, and all that kind of stuff. That's the lower end of the ultraviolet A, and they divide it A, B, and C, and C is the shorter wavelengths. That gets down to 200, I think, or 180 or something like that. It gets much shorter. And it turns out that those wavelengths, when they get really short like that, and remember, there's a correlation. The shorter the wavelength, or the higher the frequency, same thing, right? The more energy each photon has, because of we'll get in this because of Planck's constant. So it turns out the more energy it has. And these shorter wavelengths, photons have a lot of energy compared to red photons, and or infrared photons. So when they get really high energy like that, they have enough energy that they can knock when they hit, when the light strikes something, it can actually knock electrons out of atoms, turn them into ions. They call that ionizing radiation. If radiation is powerful enough that it can ionize an atom, then they call that ionizing radiation, and that's dangerous because when it happens in a biological system like your body or something, it can destroy DNA and or cause chemical reactions that can cause damage. That's why, if you go outside and you get too much sun, particularly UV radiation from the sun, it can damage your skin and give you skin cancer. That's why that happens, because of the ionizing radiation. Fortunately, the atmosphere around the Earth helps protect us from that. Just so happens that the molecules, the nitrogen and other molecules in the atmosphere, will block most of the a good chunk of the A, the longer wavelength UV, and almost all of the B and virtually all of the C radiation. But there's still enough energy in the ones that get through the atmosphere to cause skin damage, and cause damage to your, cancer and all that. So what was I talking about? So anyway, it turns out that there's a correlation, right, between. Well, let me talk about a little bit of how they discovered this, and I'm not sure about all the details, but I can give you an overview. When scientists, into all the way back antiquity, they knew that when you heated up metals and stuff, it would glow, it would emit light, and they figured out why it does that, and they plotted the curve of what happens, and what it turns out is when something gets hotter and hotter and hotter like that, the molecules are just moving all over the place, right, bumping into each other and everything. And some of the molecules are hitting each other really hard, right? They're bouncing around, and the hotter they get, the harder they hit each other. But some of them are hitting really, really hard, and some of them are just skimming each other and not hitting too hard at all. So there's a whole range of different emissions, energy levels that are emitted of electromagnetic radiation when all those little particles are bumping into each other. All those little atoms and molecules and stuff are bumping into each other. And remember, I said that when a charged particle, I'm going to refer to it. I'm going to say particle because it's easier. But it's not a particle. They're not particles. They're waves. They're matter waves. When a particle changes its vector, when something bumps it or it has a force that causes it to change direction or accelerate, decelerate, whatever, when it changes its vector, it's going to emit electromagnetic radiation. And the more it changes, if it's going really, really fast and it stops, or it's going really fast and it doesn't make a right-hand turn or something, then the more energy is emitted in that electromagnetic radiation. So when you heat something up, you've got a whole range of different energies of electromagnetic radiation. Some of them are really, really energetic, the photons that are emitted. Some of them are less energetic. So there's a whole spectrum. I think it's time for me to. You're probably getting tired of looking at my face anyway. I'm going to see if I can bring up a graph or something of blackbody radiation. Let me see if I can get this, get a browser going here and maybe go on to Wikipedia. Will have it, I think. Okay, first let me do this. Let me see if I can get this to show on my stream here. Oh, look at that. Cool. Wow. It's almost like I know what I'm doing here. All right. Look at that. All right. So, let me type in black body radiation. Black body. I think it's one word. Oh, it's hyphenated. Okay. Black body radiation. See how when I typed in black body radiation, it came up with Planck's law. We're gonna get to that. It's all part of the same thing. Okay, here we go. Oh shit. There we go. I tried to scroll and I ended up scrolling onto another window there. All right, so let me bring this up really big so we can see it. There we go. All right. For those of you who watched my last science stream, I was talking about Celsius and Fahrenheit and Kelvin. Kelvin is the absolute scale. If you go all the way down to 0 Kelvin, that means no movement, no molecules moving, nothing. Right, and they can't get to that. And I was just talking about that earlier. You can't get to 0 Kelvin. But as there's more and more movement, and then the Kelvin goes up, and that's temperature, movement of molecules, atoms, and stuff in matter. That's temperature, the average kinetic energy. Sometimes they refer to it as. So, when stuff heats up, as I just said, it emits not only in the most maximum collision of those things, it emits all of them a little bit above that and all the way down. Oh, I might have to. Oh, we got a storm going. I might have to check on something. I got a fan in the window there to cool me down, but it might be blowing rain in here. I'll be back. I got to get a little be back thing. This will just take a second. Yeah, you can look at that chart, see if you can figure it out while I'm gone. This will take 2 seconds. Okay. Let me hit you. Okay, I gotta close one more window. Okay, sorry about that. I guess if there's a storm or something coming, I just don't want to get done with the stream and walk me to the room and see big puddles everywhere from water blowing in. All right, so here's this little graph, and so when you heat something up, you can measure the temperature in Fahrenheit or Celsius or Kelvin. They measure it in Kelvin. And as it heats up, when it gets to a certain point, I think 2,500 or 3,000 Kelvin or something like that, and it glows red. And you can look at this. If you take a piece of metal and you heat it up, even before it starts to glow, if you look at it through one of those cheap cameras that I was telling you about, it's emitting infrared radiation, near infrared, before it starts to glow. So as it gets higher and higher and higher, so they're showing this little chart here of the distribution of the wavelengths that it emits. So at 3,000 Kelvin, okay, they're talking about the amount of light, the radiance, how much electromagnetic radiation is coming from the object that gets heated up. Let me see if can you see that on there? Good. Okay, my little cursor is showing up. So this one here, 3,000 K. That's 3,000 Kelvin. So if you heat something up to that temperature, that's really hot. That'll burn you really quick. That's really, really hot. That's red hot. That's why they call it red hot, right? Because it's red. When you get up to 3,000, it's red, and it's emitting wavelength or energies or wavelengths. See down here, wavelengths, in all these different areas. So this is saying This is saying microns, micrometer. So 1 is 1,000 nanometers. Remember, we're talking about how meters, nanometers, and so this one happens to be in microns. But if you add 3 zeros to each of these numbers, then it's nanometers. So, and here they even show you the visible spectrum here, where it falls from, which is about 650 or so to a little under 400 nanometers. Right, 0.5 is 500 nanometers. Right. So if you get it up to 3,000 Kelvin, most of it's going to be out here, right? But in infrared and even down to radio and all that. But there'll be a little bit of it up here that'll be, that'll be strong enough that you'll be able to see it. And when you mix all these colors together, it turns out to be red. And the interesting thing is they have green on here, but I don't know why they did that, because nothing is green. Let me do something here. Let me open this in another tab here. See if I can get a better. There we go. Get the whole thing. When you take a piece of metal and you heat it up through all the different temperatures, get it hotter and hotter and hotter, it never turns green. And they've got a green line on there. I don't know why they did that. But it never turns green because it's emitting the maximum that it gets to, or even higher than the maximum, or the visible part of it, and all of the frequencies, a little bit higher and all the way down, all mixed together. And when you mix colors, you get different colors, right? So mixing. It turns out that 3,000. I didn't check this out because I know this chart has got an issue because it's using green. But it turns out that the lower numbers, the red side of it, shows red. It shows all of the infrared and radio waves, and then red, and maybe a little bit into the yellow and stuff. And the higher the temperature gets, the more that average goes up. So you get it to this point here, and then maybe it's yellow. See, that should be a yellow line. Maybe they didn't make it yellow because it doesn't show up well on the page, but that should be yellow, right? And I'm not sure. This is something I tried to find out, and I couldn't find out. I'm not sure how they determine, what if they're taking the peak of that wave, and it's clearly not the peak, because the peak of 3000 is in infrared there, and it's not. You can still see red. So I'm not sure how they determine that. Like when you're doing the white balance on your camera, you ever do that? And it says K. That's what that is. It's this black body radiation stuff. You can adjust it. You can adjust the camera so it shows colors correctly at that temperature. That light that is emitted, incandescent light at that temperature. That's what white balance is. So there, you learned something. If you didn't know what the K, the 3000 or 4000 K or 5000 K or whatever. So when you go outside, the sun's really hot, right? It's nuclear fusion. It's really, really hot, and it's white yellow is its temperature range. So you set that at 5,000 or whatever, 4,800 or whatever the outside temperature would be. I forget what they are. And then when you got an incandescent light, indoors or something, we get LEDs now that are pretty good balanced usually, but you can get them warm. They call them warm light, which is more like an incandescent light. Then it's 3,000 or 2,500 or 2,800 or whatever, which is more red. And when you adjust the white balance on your camera, what you're doing is you're telling the camera, expect that the light is at this mix. A mix that looks like an incandescent light at that temperature, and adjust the colors accordingly. So as it gets hotter and hotter and hotter, we go to 4,000. God, I don't know if this is correct or not, but 4,000 is going to emit, all of these, but mostly the strongest is going to be here, but it's also going to have someone in this area, and in all the infrared and radio waves and stuff out here. And it turns out when you mix them all together, you get, a red or an orange or yellow. What is it? Yellow and red is orange, I guess. So, and then you heat it up even more, really hot, to 5,000 degrees Kelvin. Then you get all of these. You get into infrared light, and violet and blue and green and yellow and red, and then all the way down infrared and into radio waves. And when you mix all those together, then you get yellow, and then hotter and hotter it gets white. It just turns white after a while, because you're mixing all of the colors of the rainbow, all the visible color. When you mix all the visible colors, you get white, right? So that's what happens. That's why when something gets white hot, that means it's really, really hot, right? So, and you notice that some of these, when it gets way up there, when you get things that are really, really hot, some of it's is being emitted out here in infrared, and that's why, like welders, when they're welding metal, they got to melt the metal, you got to get really, really hot, right? That gets, I don't know what the temperature is of like arc welding and stuff like that, but because it's so hot, the black body radiation of that much heat emits enough ultraviolet radiation that it can damage their eyes. So they have to wear special filters. That's why you see welders, they got the face mask, and they have a special filter on their face mask so that the ultraviolet doesn't damage their eyes. Because the black body radiation is so hot that it has that ultraviolet waves in it. So when they discovered this, when they started figuring all this out and plotting the energies and all that kind of stuff, it didn't make sense to them. They were trying to figure out how to plot these curves, They said, okay, when the temperature goes up, we get a curve that looks like this, and then like this, and like this, and there was no easy way. I thought I fixed this. Why did that do that? There was no easy way to plot that. Let's see here. They tried different formulas. There were a couple different here's color spaces. Here's where they're showing the colors there, see? Oh, they even got 1500 on here. Look at that. 2000, 6000, and it's white by that time, right? So they tried different ways to figure it out. They had different theories. Yeah, there's a blacksmith. See, he's heating up a hunk of metal there. And look at it. See, in the middle here, where you got it really hot, it's white. And further away, as it gets cooler and cooler, you can see right there, it's white, and then it gets yellow, and then orange, and then red, and then out here, then it's emitting infrared. See? So that's kind of cool. Kind of shows you right there. Look at that. And then they show the blacksmith's color chart. This is so reliable that a blacksmith can tell the temperature of the thing just by looking at the color of it. And they know when it's at the right temperature to do certain things, bend the metal and all that kind of stuff. So that's kind of cool. What else they got in here? I was going to say oh, here we go. Lava, that's another one, right? That's really hot, so that emits light. Let's see here. Equations. Oh, that's going to get... So this is Planck's law. And he figured it out with a constant. Oh, here we go. Here's when I was looking this up, I wanted to figure out how to pronounce this guy's name. W-I-E-N. What is his name? Wilhelm. I think is his first name. And I said, okay, that's got to be wine, right? Wine or ween, something like that. And I was going to say, okay, I'm not going to bother looking up. It's got to be wine or ween or something, and nobody's going to care. But I looked it up, and it's veen. It's pronounced a veen. Veen. W-I-E-N. Veen. I couldn't believe it. That's how the guy pronounces his name. It's German, I guess, or something. So, yeah, in German, they pronounce W's V, I guess, sometimes. And in V, when two valves go walking, who knows what they do, right? That's the rule. Wiens. So, consequence of Wien's displacement law. Okay, so he had some law that so they're trying to figure out why it does that. They called it the ultraviolet catastrophe because they thought if it was just a linear function that it would just go straight up instead of having a curve like that. It kind of curves down when it gets to the ultraviolet end of that distribution. So they had all these different. This guy came up with some formula. There was several of them here. There was another one here. There was somebody before this guy, before Wien. There was another one that came out or was contemporaneous to his thing, but they didn't work. His worked pretty good on the ultraviolet side, but when it got down into the radio spectrum, it screwed up his little formula. And some of the other theories worked well on the low end and radio waves and stuff like that, but they messed up on the ultraviolet side, so they couldn't figure it out. And then this Planck guy, he figured it out. He did, and the way he did it. Let's see if I can get a picture of him. Max Planck. There's a guy. There you go. Max Planck. So that's what geeks look like in 1920s. Oh, it was in 1938. Right? Geek is a geek. I use the geek in a good way, or a geek. Geek used to be a negative term. Now it's less negative, I guess. I don't know. So there's Max Planck, and he figured this thing out. And there's aspects of this I don't completely understand, but he came up with this constant, and by plugging in this constant, called the Plancks Constant, which is a really, really, really tiny, small number, then, and with a formula, he figured it out. That it. Now I don't understand this at all. V here is wavelength, I think, or maybe frequency. I don't know. I don't understand this, and to me, you know, the actual, when you're looking at blackbody radiation, when you look at the energy of a photon, it's a linear thing. It's what is it? Energy equals Planck constant times the frequency divided by the speed of light squared, or something like that. But it looks like a linear function to me, the energy, and maybe that's, you know, the curves that you actually see there are curved. They're not. It's not a straight line. But I think maybe what that is because you're looking at the full spectrum of the thing. Anyway, I'm not really sure how that works. So maybe we can watch a video on that. Maybe I can go through, see if we can find a YouTube video on that, and maybe somebody will explain it. We'll do a live learn on that, because that's the part that I don't totally understand. Because if you just plug in a constant, and it's a fixed constant, it turns out that it's a fixed number, and Einstein figured that out, that it was an actual physical thing. Planck put it in there and said, hey, this works out mathematically. If you take a fixed number, then that means that if you multiply the frequency times a fixed number, then the energy is going to go up in steps. Right? It's not going to be continuous, because you're putting in this constant, this fixed constant. So the energy of the photon is going to go up in steps instead of being a continuous thing. And when Planck did it, he said, oh, this works out mathematically, right? They didn't have a theory yet. And then he worked with Einstein, and Einstein figured out, this is an actual physical thing. There's an actual physical thing going on here. Photons only come, or the energy of photons only occur in steps. The actual physical reality of it is that it occurs in steps. And that led to quantum mechanics, right? Quanta, a fixed thing. That's Einstein worked out the photoelectric effect because of that, and when a high energy photon hits matter and it emits an electron, it does it in fixed steps, and then the energy of electrons comes in fixed steps, and everything. That's where quantum mechanics all came from. This is where it started. Was trying to figure out black body radiation. That's what led to it. So this was the 1900s. 1900, I think, is when he actually did this. And then Einstein figured out his thing, I don't know, like maybe 3 or 5 years later or something like that. And then it just boom, man, just the next decade or so, they just went crazy and figured all this stuff out. And then we made a bomb and dropped it on Japan and killed a bunch of people. That's humans, right? They take really cool stuff and then they mess up, and then they hurt each other with it. But anyway, most of it's good stuff, right? We get good stuff from it. So all right, so that's Planck's constant, and it turns out that photons come in fixed energy amount. And they figured out this black body radiation and how that works. And what else was I going to do here? Again, light bulb. That was something. Black body. So I talked about black body radiation. Planck's constant. Maybe we'll find it. Maybe I can do that now. Let's see if I can find a video or something that explains Planck's law. I'll go to Google because they have a better search than YouTube does. Same company, but for some reason YouTube really screws up the searches. So let's see, Planck's constant. There it is right there. Yeah, and also there's a Planck length, there's a Planck size, Planck time. From that constant, they worked out a whole bunch of other stuff. You know, they said, okay, well, if a wavelength, you know, if you take the Planck constant, if the energy is a fixed amount, then that means the wavelengths have to be fixed increments. And the wavelength is a measure of the energy. That means the energy is going to be a fixed amount. Right, I did that backwards. If the energy is a fixed amount, then the wavelength is going to be a fixed amount. And wavelength is a function of time because light has constant speed in vacuum. So that means the time increments are going to be fixed amounts. And they came out with the minimum amount of time that there could possibly be, and they call it Planck time, based on the theories that we have now. There might be something something less than that, smaller than that, or whatever that we don't know about yet. So let's see. I'll just hit Planck's constant here and see if we can, and hit video and see if we can find a YouTube video or something that explains it. Oh, you know what? I actually have to go to. Wait. Maybe I can do it this way. Any source. Closed caption, quality, duration, advanced search. Oh, geez, we're getting into this. All right, I guess I'm just going to go to YouTube and try that out. See if we can get it there. Because I don't want to watch a video that's got a copyright on it. That's not, where the author doesn't give us, the producer of the video doesn't give permission for people to stream it. So. All right, let's type this again. Plancks constant explained. There you go. All right, maybe they'll explain some of that part that I don't understand. All right, so now I'll go to filters here and I'll say features, Creative Commons. I want Creative Commons that give us permission. I'm not even affiliate yet, so this isn't even commercial. This is just, so I pretty much any Creative Commons license will work for what I'm doing here today. All right, Plancks Constant. Let's see, what would be a good one here? Understanding ultraviolet catastrophe. That's what I just talked about. Energy calculations. That's what I was trying to figure out. Okay, let's see what she has here. All right. This might be kind of technical, but we'll give it a shot, right?
Lost New Hampshire Medicaid?
Where can we find a low-cost health plan?
What about a plan that covers...
Right. I can cancel out now, nanometer.
All right, let's see here. Let's see what they say here. Creative Commons attribution. Reuse allowed. Okay, that's what we're doing. Okay, they don't say what attribution they want to give, so I'll just say C. Sorensen Unruh did this video. It's her video. She owns it and she's allowing us to use it. Thank you. And I got some comments. Okay. Alright, I think that's it. So let's just I gotta listen to this and see if it actually is coming through here when I play it,
and meters, and I can get the energy.
There we go. Okay.
Of
all right, let's just watch this
photon.
for a bit.
So that's the energy of one photon. That's what I'm getting out of Planck's equation. 6.626 times 10 to the negative 34th times 2.998 times 10 to the 8th times 1 EE9.
Sorry, I must have clicked here and accidentally clicked in the middle of this thing and started it in the middle. Okay, so this is how many photons are contained in a flash of green light. That contains 189 kilojoules of energy. Okay, so this is going to be kind of complicated, but she's going to use that Planck's constant to figure out how many photons are in there. Remember, a photon we said was those steps, those individual steps. She's going to figure out how many of those individual steps there are in 189 kilojoules of energy of this frequency of light, 525 nanometers, which happens to be green light apparently. So, okay, we'll listen to it here.
Good day and welcome back to Chemistry Videos with me, Clarissa Sorensen-Unruh. We are going to talk about Planck's equation some more today. So we have this problem. Planck's equation is something that can be used in several different ways. The most common variation of that equation that we're going to use is the energy of a photon equals hc over lambda, where lambda is the only other variable here. It is the wavelength, and hc are both constant.
All right, she's putting this equation here that an energy of a photon. So the energy of a photon is going to be related to the frequency, and she uses this little symbol that she called lambda. She puts a little bend in that lambda. This is a lowercase. It's a Greek letter. Okay, you know how the Greeks had their own letters and stuff. You get alpha, beta, delta, gamma, all these different Greek letters. This is what's called lambda, lowercase lambda. Usually when you see it, and when I see it, it just looks like an upside down Y. But she put a little bend in the bottom, on the top of it there for some reason. I don't see it like that very often. It's usually just an upside down Y, but that's lambda, and lambda means the wavelength of the light. That's what lambda means. H is Planck's constant, which is a really small number, and I'm sure to figure this out she's going to tell us what that is, and C is the speed of light. So here we go.
Right? So H equals 6.626.
There it is.
Times 10 to the negative
there's Planck's
34th.
constant.
Joules times seconds. C is equal to the speed of light, 2.998 times 10 to the negative, times 10 to the negative 8. That's a way positive number, by the way. It's positive 8. It's a big number, speed of light, which you would expect because it's hard to overcome. All right, so 2.998 times 10 to the 8th meters per second is the constant we'll be using. And remember that this particular exam is hard because C in chapter 7 means the speed of light. C in chapter 6 means specific heat capacity. It's a little confusing at times. All right, so having said this, we need the wavelength. The wavelength is given to us, right? So the wavelength here is 525 nanometers. Let's go ahead and plug and chug that. Okay, why did I, by the way, know that I needed?
Okay, she's using this scientific notation here. If you're not familiar with that, and this is going to look kind of complicated. If you don't understand it, that's okay. You know, you can figure it out by osmosis eventually. But she's actually going to calculate this thing. She's going to calculate the actual energy of photon, which is going to be a really, really, really tiny number. So she's working with really big numbers and really tiny numbers here. The speed of light, and she's using scientific notation. So all that means is that 10 to the 8th just means add 10 zeros to whatever after the decimal place, whatever it is. So this is 2.998, which is essentially 3, right? It's pretty close. If we were just going to estimate it, we could just use 3 with 8 zeros after it, and a 3 with 8 zeros after it is 300 million. All right? If you write it down and work it out, it's 300 million. But she wrote it as 2.998, so it would be 299,800,000 if you had to, say it and write it out. So that number times 10 to the 8 is 2,998 with 5 more zeros, right? Because you count zeros after the decimal point. Now, Planck's constant is really, really small. And when you use a negative exponent, that means over 1. 1 over whatever the thing is. That's what the negative exponent means. So, 10 to the minus 34 would be a 1 over one with a number that's 1 with 34 zeros on it. I think I did that right correctly. So it's a really tiny, 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 tiny number. And so she's using this scientific notation 6.6286. They've actually figured this out to many more places than that, but she's working with three decimal places. So it's 6.626 times 10 to the minus 34. Tiny, tiny, tiny little amount. And you're talking about joules. So it's a joule is a really tiny bit of energy. So it's really small amount, joules per second. All right, let's listen to what she's doing here.
This particular moment, because I knew that I was using Planck's equation, mostly because I was given some kind of wavelength. That's kind of the end deal. If I'm given a wavelength on the exam, I'm either using de Broglie's equation or de Broglie's wavelength, and that's what I've been given or I'm finding, or I'm given some kind of moment and I have some kind of moment of wavelength, and I have a lot of talk about energy. When I'm given a wavelength and I have any kind of conversation about energy, I'm going to be using this equation. Okay. In this particular chapter. Alright. Or maybe I should say this particular context, if you could actually do this in the loveliness of physics as well. There's my two constants right by each other. I put my wavelength on the bottom, and lo and behold, I find out, hey, I'm canceling out stuff, life is great, seconds and seconds cancel out, meters and nanometers do not. Problem. So I need a conversion factor between meters and nanometers, and I need to make it thin. So how many nanometers are in a meter? 10 to the 9th, folks.
Okay. The reason why she canceled out those seconds is because in Planck's constant, it's a negative 10 to the minus 34. So when you use minus 34, then it's 1 over the number. On the speed of light, it's a positive exponent, 10 to the 8th. And one way of looking at that is to say the speed of light over 1. Anything over 1 is the speed of light. So you've got you got the speed of light divided by the other, because the other is a denominator because it's a minus exponent. And when you get, oops, I'm sorry, I hope I didn't blow anybody's ears out there. So you got a number on top, number on the bottom, and they both have seconds in it, and that's why she canceled out the second there, because of that negative exponent here. Okay, I just wanted to explain that, because we're talking about big numbers and scientific notation, and it's just it's kind of if you're not familiar with doing this stuff, and as I said, if I'm going to do an experiment later, so stick with us. If you don't understand this, it's okay. I mean, you might pick up some things just by osmosis. That's okay, and I'll try to explain it as much as I can as we go along. So let's let her continue with her video.
There are 10 to the 9th nanometers in 1 meter. So that's where I can go with that, right? I can cancel out now nanometers and meters, and I can get the energy of the photon. So that's the energy of 1 photon. That's what I'm getting out of Planck's equation.
Okay, I'm sorry. I'm gonna do this again. She canceled out a meter. Remember, she went with she had nanometers and meters. So it's just, nanometer is a billionth of a meter, and so she was able to cancel out some of that that exponent there. That's all that was about.
6.626 times 10 to the negative 34th times 2.998 times 10 to the 8th times 1 EE9. That's how I plug in my lovely nanometer conversion. Divided by 525, I get a cool number that's times 10 to the negative 19th. Something which we know that if it's visible light, which this checks out as visible light, it's between 400 and 750 nanometers, then I should probably get some number times 10 to the negative 19th in the joules. All right, that is cool. All right, now that I have that, I'm going to use that in this particular equation. Recognize that this could be made, this right here, could be made into a conversion factor. And what's the conversion factor we're going to do here? We're going to say that every time that you have 3.78 times 10 to the negative 19th joules emitted, that's the equivalent of the energy from one photon. Okay, now that we have this, we're going to call this good. We're going to go ahead, I'm going to leave the top equation up there, just not the answer, which we have over here as well. And we're going to use this in a dimensional analysis problem. Okay. Which is the second half of this. Okay, so the dimensional analysis problem we're dealing with here. What do we have to begin with? Well, I've already used this number in the midst of this equation. So I need to use that number. I'm going to assume that that's the initial number I was given. There it is. What am I looking for in the end? I'm looking for photons. Okay. So I need a conversion factor that goes between joules and photons. And lo and behold, I just made myself one. Wasn't that awesome? That's such great foresight there, Rissa. All right, so I know that every time that I use, or I emit, I would say emit here, 3.78 times 10 to the negative 19th joules, that's the equivalent of the energy from one photon, right? If I had a conversion factor between joules and kilojoules, I'd be done. So lo and behold, I do. Every time I have 1 kilojoule, that is the equivalent of 1,000 joules. Notice that kilojoules cancel out, joules cancel out. I'm left with photons in the end. Awesome. 189 times 1,000 divided by 3.78 EE negative 19th gives me a crazy number of photons. How about 5 times 10 to the 23rd? If I wanted to do the correct number of significant figures here, there were 3 here. There were 3 here. I should put a 5.00. So let's go ahead and rewrite that out. Photons. And that is my answer, folks. If I had been given, for instance, that this was 189 kilojoules per mole, then this would have been a different problem. Same kind of deal, but a different problem indeed. And the reason why is because you can still calculate the number of photons and the energy here. It just becomes a little bit of you're finding something different, right? So in this case, you could have said, if this was kilojoules per mole, then you could have said that in 1 mole there are 6.022 times 10 to the 23rd photons, right? And then you could have said every time I have 1 photon, that's the equivalent of 3.78 times 10 to the negative 19th joules, right? And you could have said as well that every time you have 1,000 joules, that's 1 kilojoule. The question here is, usually you're not given all of this information. Usually you're finding like the amount of energy per joule. You're not given the amount of energy per joule when you're given kilojoules per mole. And the reason why is because notice everything cancels out. What exactly am I finding here? It's a good question to ask. But the important piece here that I want you to recognize is that while this was the answer to this particular problem, you can use Avogadro's number for photons. They are nanoparticles, and they can be treated just the same way as atoms, ions, so on and so forth. Okay, so you can use them to find numbers like this in the midst, and then find wavelengths and such using the Planck's equation. So you can go backwards a little bit if you need to. But in this case, the top case, what we used to solve the problem, you did not need the conversion factor of Avogadro's number because the amount of energy you found in Planck's equation was per photon. All right, summing it up, giving you a little bit of some things to think about until I see you again.
Are you struggling in calculus? Having a hard time understanding your professor?
Are you struggling? All right, so all right, so thank you. That was I think she said her name was Lisa. Well, thank you, C. Sorensen Unruh, for allowing us to show that video. So she took that final number and figured out how many moles there were using Avogadro's number, which was kind of cool. I didn't know you could do that. That's kind of a cool thing. So I learned something. So basically, right, what she did was she just used Planck's constant there to figure out how much she knew how much energy there was. They were presented with a problem, and this is a problem. Maybe this could come up in a scientific experiment somewhere or something. You know, it's possible. You know, maybe you measure take a measurement, and you had 189 joules she had there, and you wanted to figure out how many photons there were. You can use Planck's constant to figure that out, because the energy is incremented in steps. So that's kind of cool. Didn't answer my question that I didn't understand, but maybe it was kind of cool. Maybe that was something that folks were interested in. But I don't see, you know, I would like to figure out why there's a curve, right? It's the constant. You know, if you say y equal mx, you're still going to get a line. Right? It's a linear thing. So why is it curved like that just by using Planck's constant? That I don't understand. And you know, if somebody knows, let me know, because that's the part of this whole thing that's just escaping me. Why it's a curve? Let's see, physics, Planck's law. Okay, that's kind of a long one. College of Alameda. Let's see. He's got a curve there. I think what I need to do is type in blackbody radiation, and maybe that will explain what I don't understand about it. Body. Blackbody radiation. Huh. Yeah, for some reason I'm getting a lot of my searches are coming from India and Hindi and all this kind of stuff. I happened to post a video, not even on this channel. It was a channel that's related to this one, but you know, Google and YouTube know everything about you, right? You got two different channels. They figure it out. So this is my VOD channel that I'm logged in here on YouTube, and for some reason I get, people from India and speaking Hindi or with an Indian accent and stuff like that. That's all the results I'm getting for some reason. I think it's because for some reason I posted a video once, and apparently somebody in India or something picked up on it and advertised it or something. I had like thousands of views on this video in India for some reason. I don't know why or what, but ever since then, now YouTube thinks, oh, people in India like your stuff. Maybe you like stuff from India, and so that's all that's all my results now are from. I get Hindi and all that kind of stuff. So I thought that was kind of funny. Okay, blackbody radiation explained. Right, that's what I want. I kind of explained it, but there's the part. All right, well, we'll see. Blackbody radiation explained in simple terms. We want a little bit more than simple. Blackbody radiation and ultraviolet catastrophe. Okay, that might work. This guy looks like he might be entertaining. Oh wait, now did we? Let me make. After I bring this up, I'll make sure that he's. I don't know if we had that filter in there. Oops. Okay, we stopped him. Let's see if he's got this released on. No. Shit, they didn't put that filter in. Okay, he doesn't have this released on Creative Commons. Apparently, it doesn't say that it is. All right, let's go back here. And I got to put that filter in here so we don't respect everybody's stuff there. Okay, now we got it. Blackbody spectrum of a star. Let's see. That one had some of those curves in there. See that? Maybe they explain it. It's only 2 minutes. All right, let's give this one a shot. If you have any questions, go ahead and type them in the chat. Lurkers are welcome. If you want to lurk, that's fine. You want to chat, that's fine. Doesn't matter to me. But if you have any questions, go ahead and type them in the chat. This is an inclusive channel, so I don't care if you know how to spell or get neurological issues, whatever the thing is. You're welcome here. As long as you're nice, as long as you don't do bad things. You're free to chat. All right, let me make sure this one's okay. There we go. Creative Commons Attribution License Reuse Allowed. Okay. So, attribution. This is a video by Classroom Aid. By David Butler. David Butler. Okay, thank you, David Butler, for allowing us to view your video and releasing it with Creative Commons. Title of his video is Classroom Aid, Star Color and Blackbody Radiation. All right, let's see what he's got. Back that up. I don't know. I'm going to check something real quick here before we start this video. I think my audio might be out of sync. I'm going to say something into the camera here, just to 1, 2, 3, ba 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 ba. Oh, that's right in sync. Okay, that's amazing. Half the time I do streams, most of the time I do streams, it's out of sync. But I'm right in sync as far as I can tell on my little laptop here. So that's good. And hopefully these videos are. Here I am talking. I didn't even bring the damn thing up here. There we go. Okay. Let me do this again, because I'm gonna give this guy credit here. Okay, so this is David Butler, and he released it on Creative Commons Attribution License, Reuse Allowed. And the title of the video is Classroom Aid, Star Color and Blackbody Radiation. Okay, thank you, David Butler. We're going to watch your video.
One of the very important relationships between light and matter is called blackbody radiation. Turns out that the color of most matter at high temperatures depends completely and totally on the temperature. Nothing else really matters. Take a look at this iron rod as it heats up. See how it goes from red hot at the outer edges through yellow to white hot at the center?
That's what we were talking about earlier.
If we could get it hot enough, you'd see it turning blue. Here's why. As temperature increases and the electrons start moving more rapidly, two things happen. One,
Okay, I'm going to stop this. I don't think that's true, what he just said there about it turning blue. Because when it gets hotter and hotter and hotter, it's not that there's whatever temperature it's at. It figures out a specific frequency. It's when it gets hot like that. It's that frequency plus all the frequencies all the way down into the radio spectrum. And when you mix them all together, once you get up to blue and ultraviolet, and you mix all the colors of the rainbow, you get white, right? If you took all the colors of the rainbow and mixed them, you get white. So that's why when you heat something up, it goes from first infrared, where you can't see it, and then into red, and then orange and yellow, and then white, and it just gets brighter and brighter, and then eventually gets more and more of the ultraviolet component. I don't think it ever gets blue. I think it gets whiter, brighter white, because you're not just tuning in to a specific frequency on that spectrum. You're getting the red, then you're adding to the red orange, or the rainbow, right? Which is red. Then you have red and orange. Then you got red, orange, and yellow. Then red, orange, and yellow, green. Red, orange, and yellow, blue. And when you mix those together, the way the human eye looks at it, it just goes from red, orange, yellow, white, brighter, right? So I don't think what he said there is true. Now, I may be wrong. I mean, this guy's he's a doctor, right? Did he say no? What's his qualification here? I'm not sure. I may be wrong. Maybe he's right, but I'm pretty sure I'm right. It goes because you're not just looking at the specific frequency. You're looking at all of the visible light, which turns out to be white. Okay, so let me continue this here. Sorry about that. I wanted to clear that up because that sounded like it was not correct to me.
Start moving more rapidly, two things happen. One, the object emits more radiation at all wavelengths. And two, the peak emission frequency shifts towards the shorter, higher energy blue wavelengths. As the heating starts, the radiation is all in the infrared range, so we can't see it. As the temperature approaches 2000 degrees Celsius, we begin to see red. We've seen the red star Aldebaran. It's a good example of this. By 3000 degrees, the red has morphed to orange. Arcturus is an example of this. By 4000 degrees, it is quite yellow. Capella and our own sun are yellow. Around 6000 degrees, it is turning white. The star Sirius A is an example of this. And by 10,000 degrees, it has a distinct bluish color. Spica is a good example of a blue star.
Okay.
So the bottom line is, measure the color of a star by the frequency of the light it emits, and you've determined its temperature. It's that simple. Now that we know star temperatures via their color and luminosity via their parallax distance, we can build a diagram I mentioned in the introduction.
Say goodbye to old, costly cable TV once and for all. This revolutionary invention.
So I guess it is when you get into fusion. I guess that happens. Apparently, it does turn blue. That's true, because you do. There are some stars that do have a little bit of a bluish tint to it. These 2 ads I gotta go through here. 2.5 minutes. Okay, while this is going on, I'm gonna go back to here. Yeah, so in ordinary ordinary temperatures that you have on Earth, it only stays white. But in astronomy, yeah, that makes sense. That if you get up to really high temperatures that you can't have here on Earth, that it would turn blue. Because most of it was in ultraviolet, and it peaked around blue or in ultraviolet. But it's not blue. It's like a bluish white. Oh wait, I can skip this ad. Wait a second. Just let me skip it here. Okay, that was the end of the video. Okay. So cool. So we learned about that. Didn't explain why Planck's constant explains the curve of the blackbody radiation. It didn't explain that, and that's what I want to explain. That's what I want to learn, is why Planck's constant, which you would think would be a linear function, makes that curve like that, and I still don't understand that. So if anybody knows, I got some chat here. Hang on just a second. Let me catch up to chat. We got a raid. Oh, thank you. My first raid. This is the first time ever. I've only been streaming for 2 or 3 weeks now, and this is my first raid. Very cool. All right, let me go through chat here. Zach App. Oh yeah, Zach App. I've seen your videos before, your stream. Thank you for raiding. Let me. I can try out my shout out function here. Let's see if it works. I might have to do an @ sign here. I appreciate you giving me the raid there, guy. Let me try it this way and see if it works. I'm still getting my sea legs here on streaming. Okay, yeah, it gave you a shout out there. Cool. Okay. So we're talking about technical stuff. I'm talking about you can see in the title there. Planck's constant, blackbody radiation, that sort of stuff. It's a science stream. I stream everything from, I do some IRL, I do mostly science and technology. Got a sci-fi movie night, which might morph into just a plain old movie night. Got animals around here. I live on a donkey farm in rural New Hampshire. So got lots of animals around here. Let me go through the chat here and see. Okay, right, Raider. Really appreciate the raid there. Now I don't have any moderators, so everybody be nice. Geez, I know you've got a nice community there, Zach App. So I know. Am I pronouncing your name right, Zach App? I think I am. Everyone knows stars are just holes poked in the firmament. Yeah. Yeah, we liked your go vegan and stay woke tags. Cool. Yeah. All right. Yeah, I've been vegan for over 40 years. So when I first became vegan, nobody knew what vegan was. I didn't even know what a vegetarian was when I became vegan. So yeah, I did it for animal rights. Right, I was into animal rights in the 80s and 90s, and so raids from fellow vegans. Mushroom back the rebro. Yo, respect. Yes. All right, nice. Cool, yeah. Yeah, so I thought about doing maybe even a cooking stream or something, but that gets really complicated. I'm gonna have to get do a lot more on this streaming learning curve before I figure out how to do a cooking stream. And I'm not really set up. I'm in an old house here, and it's really not set up for doing that kind of stuff, cooking streams. But I did a vegan stream. There was a recent scientific paper that was written on veganism. Sorry for the diversion here a little bit for you guys, but we'll get back to the Planck's constant and blackbody radiation. But I did a stream on this vegan paper that came out, or it was a paper about veganism, and it compared twins, which is like about as good as you can get in studies. Compare twins, and it kind of eliminates the DNA differences between the subjects of the experiment. And so they compared twins, and one twin ate a healthy, quote unquote healthy omnivorous diet, and the other twin ate a vegan diet. And then they looked at their telomeres and all these different parts of their DNA in their cells and all this stuff to figure out their biological age. You have your chronological age, and then there's biological age, which is based on different things they can measure in your cell. And they found that in the vegan diet, the cells were healthier, and telomeres were a little longer, and all that kind of stuff. So, and we already know, right? There have been studies that say that vegans live, like a decade or 13 years or something longer than typical omnivore. So this guy just did it, really. It was a small sample. I forget how many it was, 23 people or something like that. And when they're doing those kind of in-depth measurements, they can't really have large N on our studies. But that was kind of cool. So we talked about that, and I don't know, did we show a video? Yeah, we showed a video. Somebody did a video. Some YouTuber did a video on the study, so it was pretty cool. Let me get into do more chat here. So most of my streams have 0 chatters, so I'm gonna have to. And I have dyslexia, so this is gonna be a kind of a challenge. Yay! Okay, Zio Duck says, "Yeah, that's often interesting. Who doesn't like food? Yes, everybody likes food." Teo says, I'm sorry I'm mispronouncing your names properly, but I have dyslexia. I can't read very well. It's so much easier to go vegan these days. Oh yeah, when I became vegan, this was back in the early 80s, 81, 82, something like that. I mean, it was nothing. You go into a store, and I couldn't even buy pizza or spaghetti sauce. Every single brand of spaghetti sauce had meat in it, or and stuff had lard in it. It was really difficult. Of course, there were hardly any vegetarian restaurants at all. It was really a challenge back then. The only company that had anything was Loma Linda, which was a company or something that was, or nonprofit group or whatever, that made these vegetarian products for Seventh-day Adventists, because Seventh-day Adventists, the strict ones or whatever, have a thing where they have to eat vegetarian apparently. So there's a company called Loma Linda who came out with these products, and they were expensive and not, anyway. So now it's so easy. I mean, they got vegan cheeses that melt. That's amazing. Greeting. Let's see here. Let me go through the chat here really quick. Edicator. Greetings. Yeah, greetings. Thank you. Nice. My mom was vegan. Okay, this is Kate Triss Fire. Nice. My mom was vegan, vegetarian, lactose intolerant, and she has celiac. I don't somehow love bread, but yeah, grew up eating pretty entirely veg. Cool. Yeah, so you'll probably live longer. Let's see. We got Zeoduk. But one twin is a marathon runner, and the other one, yeah, there are environmental factors, but what they eliminate with the twin study, of course, is the genetic factor, right? You know, some. Let's see. Okay. Let's see. You got it right. Okay. Okay, Trisfire. I sneak some good seafoods if I'm traveling. But yeah, a lot of fishitarians, pescatarians, whatever they call them. Yeah, various diets affected the environment differently. He even has a good attitude about vegan cheese. Cool as hell. All right. Katie, if that's easier. Usernames are hard to pronounce sometimes. Yeah, it's kind of hard. And I have dyslexia. I have social dyslexia too. So, social cues. Sometimes I can, sometimes I can't get those. So, and dyslexia, especially on reading. Like if I try to read a novel, forget it. I can't dialogue and all that. I can't figure that out. All right, we got through chat there. All right, so we'll get back to this. So if you like that kind of stuff, you like veganism, you like, I'm not even a affiliate or anything. I got to get more followers, so hit the follow button if you like veganism and science and technology and sci-fi movies, film, all that kind of stuff. Last night I think it was? Last night or night before, I did a breakdown of iRobot with Will Smith. And went through that whole film and showed clips and stuff and talked about it. So that's the kind of stuff I'm into. And right now it's a little choppy, it's a little scuff. You know, I'm 2 or 3 weeks into this, so. But hopefully I'll get better and better as we go along. Swiss R, welcome in. Thank you. All right, so I'm going to see if I can find another. I want to bring up my browser doohickey here again and see if we can find a video. What I'm trying to find out here for you raiders, we're doing this thing. We explained what the Plancks Constant was, which is a fixed, really, really tiny number that turned out to explain blackbody radiation, which is anything that gets hot radiates electromagnetic energy. Me, everything, my mouse, my webcam, my glass of water, everything emits electromagnetic radiation. We can't see it until it gets really, really hot. So like if you heat up a piece of metal or something and it gets up to, like over 1,000 degrees or whatever Celsius, I forget what the number was, we figured it out there, 2,000 or 2,800 Kelvin, which is it's just another scale, temperature scale, then it starts to get hot enough that the molecules move fast enough that when they bump into each other, they emit electromagnetic radiation that's high enough energy that the frequency is higher and the wavelength is smaller, and it gets into the visible range. So that's kind of that's a 2 seconds summary of what we just covered so far in the stream, the first hour or so of the stream. So what the question that I had and I couldn't figure out, and I'm doing a live learn on here right now, is there's a curve to that black body radiation. As it moves up, it still remains a curve. It has a peak, but instead of being a straight line from low frequency has low energy and high frequency has high energy, it has a curve like that. And I'm trying to figure out how the Planck's constant explains that curve. Because when you look at the formula for the energy of a photon using and we just went, before you guys rated in, we watched a video where a woman actually figured that out on a blackboard and went into detail about how to figure out the energy of the photon. What she figured out was the number of photons. She figured out the energy of the photon, and then based on the energy of the total energy of light, she figured out how many photons were in there. So why does that curve, though? Why do you get a curve if it's a linear function, and that's what I don't understand. And I'm trying to find a video that can explain it. If somebody knows, yeah, feel free to type into chat. Let me go through chat here really quick here and catch up. All right, you got it right. Okay. I sneak some good seafood. Okay, we talk about veganism. Good attitude. Okay. Pronouncing names. No worries. We're all variously fumbling. Yes. Okay. Thank you. Cool. So, are you religious? Oh yes, I got AMA on there, don't I? Yeah, but that's really hard to explain. Kinda. Yeah, I guess I am. I don't go to organized religion because of my condition here. It's difficult for me to do social events and stuff like that, and it just doesn't work out well for me. I've done it over years and stuff like that. It's just, organized religions certainly, and my particular beliefs are, as far as I know, nobody believes this, what I believe in terms of religion. I haven't found anybody who believes what I believe in religion. One of these days, maybe I'll do a stream on that. Let's see. Sweet. Patrick. Cool, Will. Hope to catch you soon. Okay, Zeoduck. The 3 laws. Yeah, we talked about the 3 laws on that video. That review we did of iRobot. You can check out the VOD on that. All my VODs are up on YouTube. I got a link in there, on my Twitch About page there. You can find all my VODs out there. So far, YouTube has let me put up there. They hasn't censored anything. I kept the fair use clips from the iRobot as short as possible, and cut everything off, or to try to stay within the stupid IP laws. Okay, OBS has some good sound filters. If that's the streaming platform, yes. Yeah, I haven't. Are you guys getting a good reading of my mic? I think it's loud enough. I thought about running my my mic through a filter, and I'm trying to avoid that because it takes CPU and everything else. Yeah, your mic is very clear. Okay, thank you. So at some point, man, I might do that. I've got this cheap. I'm really cheap. I spent $60 to get into streaming. That's how I did this, just using junk that I have around here, an old CPU. I just bought. It had 4 gigabytes of RAM in it, so I brought it up to 8 gigs of RAM, and put an SSD in it, and that's about it. And it was VGA, so, but it turned out I had a DVI port on it that I could get HDMI. So I'm about as low as you can get in terms of CPU and all that kind of stuff. I'm not a wealthy person, so this is what we got. So I got to try to work it out any way I can. This little mic I've got here, it's look at this. It's this little tiny mic, a lavalier mic that I bought for $10 on eBay or something. USB mic, and I stuck it on a spring, and it's really funny, but it works, right? Yeah. I want to get a big mic. I want a big mic. Maybe I'll build one on stream. We'll see. All right, so let's see. Blackbody radiation. Let's see what this one is. Now, see, I don't know if I can click this or not. All right, let's bring it up here, and I'll check and see if they're giving me results that are. Okay, Creative Commons. No Creative Commons. So you'd think if I told it that I wanted to filter by only Creative Commons, but it gave me results that weren't. So I got to go back to my original thing here. I think all these are Creative Commons. Classroom. All right. Why the bright sun is considered a black body. Okay. I don't know if that's going to explain it. Ultraviolet catastrophe and the birth of quantum theory. Okay, this might have it. Because I'd explained early in this stream here that Planck's constant and black body. So this is going to be kind of redundant to what I did earlier in the
Physical
stream, but for you
objects,
readers,
regardless of their
this will
temperature,
kind of fill you
emits
in, right?
electromagnetic radiation with specific range of
Hang on just a
wavelengths.
second. Let me stop that and make sure that this is Creative Commons. Creative Commons license attribute reuse. Okay, attribution. The attribution is boyfriend NI blue fairy. All right. Ultraviolet catastrophe and the birth of quantum theory. Okay, thank you for boyfriend Ni blue fairy. Thank you for putting this video up on Creative Commons so we can watch it here on stream. All right, let's see what you got to say about this. All right, so we'll watch this, and I'll stop it if there's anything that I think we need to, think about or explain or whatever.
Based on experiments, the object emits electromagnetic radiation with shorter wavelength when its temperature increases. Since this object emits electromagnetic radiation, let's call this object as emitter. On the other hand, if an external electromagnetic radiation lands on the surface of a physical object, some of it is partially absorbed and some of it is partially reflected. Of course, some absorbed electromagnetic radiation is emitted to the external surroundings.
Okay, can everybody understand his accent? Some people have difficulty with different accents and stuff. I can understand him pretty good, but if you do, let me know, and I'll try to explain more that way.
There is this theoretical object called blackbody that literally absorbs all electromagnetic radiation incident on it, and then emits some of the energy in the form of electromagnetic radiation. In other words, there's no reflection going on when it is illuminated by an external electromagnetic radiation. Hence, it is a body that is a perfect absorber and a perfect emitter. If the temperature of this black body increases, that's because it keeps on absorbing electromagnetic radiation. If the temperature of this black body remains constant while absorbing electromagnetic radiation, then this means that it effectively emits the radiation to its surrounding to maintain the temperature. Of course, a black body is just an ideal model. In reality, some electromagnetic radiation illuminated on an actual body escapes in the form of reflection. And to effectively study the electromagnetic waves emitted by a black body, we must be able to siphon these electromagnetic waves into a sensor and record its physical characteristics like intensity, etc. To physically implement or realize a black body where we can siphon emitted radiation into a sensor, consider this cavity radiator with rough and blackened inner surface to effectively trap the incident radiation and control the direction of electromagnetic radiation emission. This is a container with a small hole where an electromagnetic wave can enter and be absorbed or reflected along its inner surface. Now in this setup, the reflection should be minimal and majority of the light rays inside it that you are seeing is actually emitted and not reflected by some particles lining along its surface. Now what you're seeing here is ideally the electromagnetic waves emitted by the inner surface. Sensors can easily detect the electromagnetic wave that will be emitted by this radiator because it will specifically come out from this hole. This radiator satisfies the condition that a black body is a perfect absorber because of its trapping ability. There are two things we can measure from this setup. The first one is the temperature of the black body, and the second one is the intensity of the emitted radiation as measured by the sensor. The intensity measured by the sensor is a function of frequency and temperature. Here, the frequency nu refers to the frequency of the incident electromagnetic radiation, and the temperature refers to the temperature of the black body. Let's plot the frequency versus intensity graph of a black body radiation. From 300 gigahertz to 430 terahertz, this region is called the infrared region. From 430 terahertz to 790 terahertz, This region is called the visible region. From 790 terahertz to 30,000 terahertz, this region is called the ultraviolet region. When they feed the radiator with electromagnetic wave with a frequency below the visible region cutoff, the intensity plot for a radiator with temperature of 4,000 kelvins looks like this. And this is consistent with the fact that as you increase the...
Okay, I'm going to stop this real quick just to explain something. He's got down here at the bottom, he's using terahertz for wavelength. Very often, and in most of the examples that I've had up until now and the way I've been talking about it, they use wavelength, and wavelengths and you know, the higher the frequency, the shorter the wavelength. That's how it works. And the visible spectrum is between on the low end, the longer wavelength is going to be around 700, 680, 700, something like that. Nanometers wavelength. Nanometers really small. But and then when you get up to the violet and ultraviolet, then it's 400, and beyond 400, then about they consider ultraviolet. 400 being 400 nanometers. So a lot of times you'll see where they're talking about light, especially on the higher end, they use wavelength, and they'll talk nanometers instead of, and this guy's talking about terahertz, which is less common, but I just wanted to explain that. So if you see it other places, you know, other charts and stuff like that, they call it nanometers. They do it in wavelength instead. So I'll continue this again.
Frequency, you are increasing the energy fed into the radiator, and hence the intensity it emits increases as well. For a temperature of 5,000 kelvins, the plot looks like this. There were two scientists, Rayleigh and Jeans, who provided an approximation for these results. And their equation is called the Rayleigh-Jeans law. When they used this equation, they predicted the graphs for 4,000 kelvins and 5,000 kelvins at the ultraviolet region, and these are shown with these dotted lines. They even predicted the graph for 6,000 kelvins, and it looks like this. However, based on experiments, the graph for 4,000 kelvins gradually decreases, and it looks like this, and not exponentially. Also, the graph for 5,000 kelvins dies down at higher frequencies. What's more surprising is the result for 6,000 kelvins. Also, based on the experiments, when the frequency is increased beyond the visible range, the intensity decreases. If you look at the Rayleigh-Jeans equation, notice that intensities diverges to infinity for high frequencies, as if the radiator releases disastrous amount of energy. And this catastrophic event takes place at the ultraviolet region. That's why this phenomenon is called the ultraviolet catastrophe. To explain this sudden drop of intensity at the ultraviolet region, Max Planck, a German physicist, made an assumption that atomic oscillations inside the cavity walls can oscillate in such a way they possess discrete amount of energy. With this assumption, he was able to derive what is known as the Planck's law of blackbody radiation. And this equation accurately predicts the results of the experiment, especially the decrease of output intensity in the ultraviolet region. From Planck's law, we can derive
Okay, so this explains it a little bit better. What I was looking at was a linear function, which was the relation between the wavelength or the frequency and energy. So the higher the frequency, the more energy, and because it's discrete, so each photon, the energy of a photon, which is that big complicated one that we did equation that the woman explained earlier. So the higher the frequency of a photon, photons are individual packets of electromagnetic energy, and the higher the frequency, the higher the energy of the photon, and that's a linear function. But this Planck's law, this is different. This is a different equation altogether, and it's exponential, so that does make sense. So this kind of explains my answer, I guess. I don't understand that equation, but or how he derived it or whatever. But it's clearly not a linear function, so that kind of explains it a little bit better for me. But I'll go ahead and continue this.
Wien's displacement law and Stefan's law. In Wien's displacement law, lambda sub max is the wavelength law. In Wien's displacement law, lambda sub max is the wavelength at which a black body radiates.
Yeah, I explained earlier before the Raiders came in that this guy's name, Wilhelm Wien is how you pronounce it. I think he's pronouncing it Wien, but it's Wien with a hard E. As German.
It's most strongly
so
for a given temperature T.
Yeah.
On the other hand, Stefan's law allows us to calculate the total power of blackbody radiation emitted across the entire spectrum of wavelengths at a given temperature. In these plots, this power is represented by the area under the blackbody radiation curve for a specific temperature. Here, sigma refers to Stefan-Boltzmann constant, which is equal to 5.67 times 10 raised to negative 8 watt per m squared times Kelvin raised to 4. A is the surface area of the black body, and T is the temperature in kelvins. Let's return to the radiation curve. This positive slope, where intensity increases when the frequency of the supplied electromagnetic wave is increased, is easy to comprehend. But this side of the curve is not easily explained by classical physics. Going back to our cavity radiator, Max Planck assumed that a black body consists of many charge oscillators that can take on specific energies. In his original paper, it wasn't specified if this charge oscillator is an atom situated on its lattice or an electron that is initially on its ground state. Either way, both particles can absorb, emit, or ignore an electromagnetic wave. If we're dealing with an actual atom, remember that an atom can be influenced by an external electromagnetic radiation because atom consists of charged particles like electrons and protons. Max Planck assumed that charge oscillators can only vibrate in such a way it possesses discrete amount of energy, or specifically, an integer multiple of h times f, where h is equal to 6.626 times 10 raised to negative 34 joules second, and f is the frequency of vibration. For example, if h times f for a particular oscillator is 2 electron volts, then the particle can only have energies of 2 electron volts, 4 electron volts, 6 electron volts, and so on. When an atom absorbs an energy from electromagnetic wave, it momentarily moves away from its equilibrium, and then it releases the energy and then returns to its equilibrium position. This repeated process of absorption and emission makes the particle seem to vibrate with respect to its equilibrium position. Similarly, when an electron, initially on its ground state, absorbs energy from electromagnetic wave, it jumps from its current state, releases the energy, and then returns to its previous state. Suppose the upper bound of our particle is 4 electron volts. Beyond this energy, the particle will not absorb the energy. If this exceeding energy is multiple of hf, the particle can absorb the energy, but it will use it for translation. In other words, when the energy supplied is beyond the upper bound, this can possibly be used by an atom to break free from the lattice point. This can be viewed as if the solid is melting, or it can be used by an electron to be ejected from its possible shells. So to explain the sudden drop, when the frequency or energy of the incident wave is not in the allowable energy states of the particle will simply not absorb the energy, and hence no emission occurs. And this will register as a low or zero intensity level on the sensor. Or when the energy of the incident wave is beyond the threshold of the particle, but still a multiple of the particle's h times f, then it will be used by the particle to completely break from its lattice point or various shells. In this case, there will be no radiation because the particle is no longer there. And this will register zero intensity level on the sensor. This quantization of energy is the start of a silent revolution in physics, wherein
Yeah, that point that he talked about right there, that's ionization. If you have a, he was talking about strong electromagnetic radiation causing an electron to leave an atom. That's called ionization. So if you have a really high energy photons, that means photons that are a higher frequency than even visible light, has to be up in the ultraviolet range, at least. Then that's called ionizing radiation. You know, light, everything is radiation, right? But if it gets higher, if it gets above the visible range and even above the low end of the ultraviolet, like in the UVB, they call it UVC, that area, then it starts becoming ionizing radiation. And that's a problem if you're a biological organism, because it can cause your DNA to mess up. It can do all kinds of stuff to you by ionizing the molecules that make up the cells in your body and cause damage. And if you live where there's a lot of sun, you get skin cancer and everything else. Fortunately, the atmosphere of the Earth filters out most of the ultraviolet radiation that comes from the sun, and almost all of the really damaging stuff, the UVC. But there's still a little bit that gets through, and that's why people get skin cancer. So that's what he was talking about there. That's ionization, where it causes an electron to completely go fly away from the atom.
At certain scales and conditions, the transfer of energy is no longer continuous, but occurs in discrete amount or packets of energy. And this is one of the underpinnings of quantum physics. This problem is from OpenStack's University Physics Volume 3, Chapter 6, Photons and Matter Waves, Problem 55. A 200-watt heater emits a 1.5 micrometer radiation. What value of the energy quantum does it emit, assuming that the specific heat of a 4.0 kilogram body is 0.83 kilocalorie per kilogram times Kelvin? How many of these photons must be absorbed by the body to increase its temperature by 2 kelvins? How long does the heating process in B take, assuming that all radiation emitted by the heater gets absorbed by the body? So imagine in this problem we have a heater and it radiates an electromagnetic wave. In part B, let's just represent this 4 kilogram body with a solid cube. So according to the problem, this electromagnetic wave has a wavelength of 1.5 micrometer, and this heater has a power output of 200 watts. So in part A, we would like to calculate for the value of the energy quantum. Actually, the energy of quantum radiation is given by this expression, which is equivalent to E sub 1.
Are you struggling in your calculus class? Do you have a hard time understanding your instructor?
Sorry about that, guys.
Do you wish there was a simple...
So from Max Planck's expression, we can calculate the quantum energy when we are given with the frequency of an electromagnetic wave. So for this problem, we will calculate for the minimum quantum energy that an electromagnetic wave can have, which means that we have to calculate for E sub 1. To calculate the numerical value of this quantum energy, we have n equals 1 times the Planck's constant and the frequency. In this problem, we assume that the electromagnetic wave travels in air, which is
this little thing here, this 6.626 times 10 to the minus 32 joules per second. That's the Planck constant. That right there is the Planck's constant. He didn't explain that too well, but that's what that is right there. Tiny number. See, minus 10 to the minus 39. So when an exponent is minus, then it's 1 over, right, the number. So this is a tiny number, this Planck's constant. So I don't know. This problem he's doing here, I don't know how relevant it is, but we'll go ahead and we'll let him go ahead and finish it here. He's he's about halfway through his video here, but we'll just let him go through it and explain it. Maybe we'll find something. Maybe he'll say something interesting here. I
near
don't know. We'll see.
vacuum. So we can use the formula for the speed of light, C. Remember that all electromagnetic waves travel in the speed of light in vacuum. So C equals the wavelength divided by the period, or lambda times frequency, because the reciprocal of period is frequency. Given this expression, F is equal to the speed of light divided by lambda. So I can plug this expression here. I'm supposed to have C over lambda here, but I'll directly write the numerical value, which is 3 times 10 raised to 8 meters per second, divided by lambda, which is 1.5 micrometer. And we have a numerical value of 1.3252 times 10 raised to negative 19 joules. We can convert this into electron volts by dividing this with 1.6 times 10 to the negative 19 joules, and we end up with 0.83 electron volts. We might have different value for this depending on how you round off some of the given. In part B, we are given with the specific heat of this object. We can assume that the electromagnetic wave is completely converted into thermal energy when it is absorbed by the object. And from thermodynamics class, the thermal energy is equal to mc delta T. And based on the given, the object is able to absorb this electromagnetic wave, and because of this absorption, its temperature is increased by 2 Kelvin. So delta T here is actually equal to 2 kelvins. Now, in part B, we are asked to find the number of photons that must be absorbed by the body to increase its temperature. So in photoelectric effect, you learned that according to Einstein, electromagnetic waves are also quantized, and the particle of light is called a photon. So if one photon possesses E sub 1 of energy, then to calculate the number of photons that's being absorbed by this object, by virtue of conservation of energy, if after absorbing all this electromagnetic wave or all the photons landing on this object, then we just have to divide the total energy of that object with the individual energy of photon, and then after that we will be able to calculate for the number of photons that is being absorbed by the object. So in other words, the total energy absorbed by the object coming from the electromagnetic radiation is fully converted into thermal energy. And to calculate for the number of photons, we have to divide this total energy with the energy of a single photon, which is E sub 1, and we will be able to calculate the number of photons absorbed by the object. So let's calculate for the total E. So the mass is 4.0 kilograms times the specific heat, which is 0.83 kilocalorie divided by kilograms times Kelvin times delta T, which is 2 kelvins. So when these kelvins cancel out, kilogram cancel out, and we end up with Q equals 6.64 kilocalorie. Now from thermodynamics class, recall that 1 kilocalorie of energy is equal to 4,184 joules of energy. So to convert this into joules, Q equals 6.64 kilocalorie times a factor wherein that factor has a kilocalorie in its denominator, so we can cancel this out. So using this factor, 1 kilocalorie equals 4184 joules. So Q equals 27,781.76 joules. So to get the number of photons, we just have to divide this total energy with this energy. So again, I need to convert this energy into joules because my denominator here is in joules. So I'll divide this with this value, and I'll end up with 2.1 times 10 raised to 23 photons. So in part C, how long does the heating process in B take, assuming that all radiation emitted by the heater gets absorbed by the body? So we're actually looking for the amount of time to absorb such.
Okay, what he just did there, I don't remember if you guys, the raiders, if you saw the woman who was explaining a similar problem to this. She was explaining how to determine the number of photons that are emitted by or a light source or a radiator, and she figured it out by the you measure the number of joules, the total energy coming from this little thing, and it had a specific frequency, which was a green light, and she calculated how many photons there were that were emitted by an emitter. Now he's doing the kind of the opposite. He's calculating how many photons are absorbed by a mass. So it's kind of the same problem, but a little bit different. And at the end, she figured out how many moles based on Avogadro's number, which I've never heard anybody use Avogadro's number to express photons, but apparently you can. It's particle, right? So I guess you can. No, I don't know if he's going to do that here, but we'll continue. I'll continue the video here and see what he does next.
Energy. And from our discussion in mechanics, power is equal to the energy transferred per unit time. So rewriting this, we have T equals total energy divided by power, and the total energy absorbed by the object is this one. So this is equal to 27,781.76 joules divided by power is already given, 200 watts, and time is equal to 138.91 seconds, or 2 minutes and 38 seconds. So we might have different value depending on how you round off some of the given, but based on this calculation, time is approximately equal to 2 minutes and 38 seconds. This problem is from OpenStack's University Physics, Volume 3, Chapter 6, Photons and Matter Waves, Problem 57. For what temperature is the peak of a blackbody radiation spectrum at 400 nanometers? If the temperature of a blackbody is 800 kelvins, at what wavelength does it radiate the most energy? So from our discussion of blackbody radiation, if the vertical axis is our intensity and the horizontal axis refers to the frequency of the input electromagnetic wave, then the blackbody radiation curve looks like this for a given temperature. But if our horizontal axis is converted in terms of wavelength, then the curve is just reversed since frequency and wavelength are inversely proportional to each other. And the relationship that relates wavelength with temperature is the Wien's displacement law. Lambda sub max times temperature equals 2.898 times 10 raised to negative 3 meters times Kelvin. Apparently, lambda here is in meters and temperature here is in kelvins. So in part A, what temperature is the peak of a blackbody radiation spectrum at 400 nanometers? So for example, we have this plot, and at a wavelength of 400 nanometers, this curve has this peak. So we are asked to find the corresponding temperature for this curve. So based on this Wien's displacement law, temperature is equal to 2.898 times 10 raised to negative 3 meter Kelvin divided by lambda sub max, which is, in this given, it's 400 nanometers. And plugging in the values, we have 7,245 kelvins. In part B, if the temperature of a blackbody is 800 kelvins, at what wavelength does it radiate most energy? So in this problem, we can use Wien's displacement law to calculate for the lambda sub max, assuming that the blackbody has a temperature of 800 kelvins. So using this same equation, lambda sub max equals 2.898 times 10 raised to negative 3 meter times Kelvin divided by 800 Kelvin equals 3.62 micrometer. So we might have a slightly different value depending on how you round off some of the given, but in my calculation, lambda sub max is equal to 3.62 micrometers. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching! If you're a bit
All right, so that was kind of cool. That last one, I didn't totally understand it, but yeah, when he was talking about lambda, he kept saying lambda. I don't know if I don't think he explained it very well. I explained it earlier, but lambda is a Greek letter. Obviously you got alpha, beta, delta, gamma, all that. Lambda is one of the Greek letters, and a lowercase lambda, which looks like an upside down Y, that represents wavelength. So that's what he was. That's why he kept saying lambda all the time. He's talking about the wavelength. So that's kind of cool, and that kind of explained it, because that's a totally different equation than all of them that I had seen before. That Planck's law is pretty complicated, that equation, but it was a linear. I mean, it wasn't a linear equation at all. It was exponential, so that would explain that curve. So that's kind of cool. So we learned that. What else was that? Oh, the invention of light bulb. I was going to talk about the invention of light bulb. Let me bring up a Wikipedia article on that. Let's see here. Max Planck. Max Planck Society. Okay, let's see. Incandescent light bulb. Incandescent light bulb. So incandescent light bulb, the old-fashioned light bulbs before they came out with LEDs and or compact fluorescence or any of those, was just a piece of wire that they put electricity through, and everything has resistance in it unless it's a superconductor. Everything has resistance. Even a copper wire has a certain amount of resistance in it. And if you have a small enough piece of wire and you put enough electricity through it, all the electrons trying to get through the wire heat up the wire. And if you heat it up hot enough, then it starts emitting radiation, like the blackbody radiation. That's what an incandescent light is. The light bulb, the old-fashioned light bulb. Oh shit! I didn't turn this on. Sorry about that. Let me. Sorry, still learning. All right, there we go. So here's the Wikipedia article. So this is a total application of that blackbody stuff. By running electricity through the this little coily wire here. They got a close up of it here. They coil it doubly so they can get it even longer. Right? They coil it really, really, really small. This is electronic scanning. It's a really close up of this thing, super microscopic close up of the filament of a light bulb, and it's curled twice. It's curled in small curls, and then they take that curly thing and then they curl it again. And that way they get really, really a long length of the filament. And then when you run electricity through it, it's got resistance. Electrons go through that, make it heated up, and when it gets hot enough, then it emits energy, EM. And this is why incandescent light bulbs they use the term warmer, meaning that it's more red in color than fluorescence or the newer LEDs that are full spectrum, full white, is because they only heat up to a temperature that makes them kind of reddish white or reddish yellow, something like that. And our eyes adjust a little bit, but cameras can't. Cameras don't adjust. Our eyes and our brains can adjust to the light when it's an incandescent light, and it kind of looks normal to our eyes and our brain. But cameras can't, and that's why in cameras they have that adjustment, the white balance adjustment, and that's color temperature. And when you adjust it, if you do it manually, the newer cell phones and all that, the computers do all that work for you. But if you have one with a manual adjustment, you can adjust the white balance manually, and you can type in a number that's a K, you know, that 500K white balance or color temperature, whatever. What that means is that the white balance that you manually type in there, you're telling the camera to make adjustments to make the colors look natural to us based on a light source at that color temperature, like a blackbody radiating at 5,000 degrees Kelvin, or in the case of a incandescent bulb, what is it, 2,800 or something like that, or whatever the number is. So that's what white balance is. That's what color temperature is. It goes all the way back to this blackbody radiation. And so the old incandescent, they got hot, but they didn't get hot like what goes on inside of a fluorescent bulb or something like that. They just heat up a filament, and the way that they keep it going. Now the experiment that I wanted to do here, maybe I can do that now. This is the first. I guess what I can do is duplicate the first steps that they did in inventing the light bulb way back when. And by the way, Edison didn't invent the light bulb. Maybe you didn't know that. He just exploited it. He started a company. There were guys that came before him. Maybe they here, let me scroll down to history here. So there's all, it goes back to 1761, right? This guy demonstrated heating a wire to incandescence. Exactly what we're talking about. This is the experiment that we're going to do tonight, is the thing that this guy did in 1761. This was the first step in the invention of a light bulb. So this guy heated up a piece of wire until it glowed using electricity, but it melts. It melts right away because there's oxygen in the air, and it burns, and it just burns up the metal. So that's what this guy did. And later on, they put the filament inside. Let's see. Presence of, okay, limelight became popular. Okay. I'm trying to read this really fast here. Yeah, and then they tried to use platinum, because platinum, you can get platinum has a higher melting point, so it won't melt, but it's real expensive, so they couldn't really use that for lights. And then they had an arc light, and they had all these different things. But let's see if I can set up this experiment now, which is this first step that this guy did back in whatever. We'll take a piece of wire and we'll heat it up until it glows, and we'll see what happens. All right, let me see if I got this, if this is going to work here. What I did is I got this old camcorder here, and I have this is a transformer from a train track, a train set transformer, and it's got little AC outlets here. One of them is constant 18 volts or something like that. And this one, it has a variable. So what we can do is hook it up and then crank this up until the thing glows, and you'll see what happens. I tried this earlier and it kind of worked. So, and I'm setting this on top of a there we go. Okay. And I'll just slide this over here. Can you see that on the monitor? There it is, yeah. Let me get rid of that Wikipedia article. This is really cool, so you might want to stick around for this if you can. All right, so I've got, that shows up really good. Okay. So here's the setup, right? I've got this transformer here. It's got the little connections on the back. I'm gonna hook a wire up to a couple of these connections here. I've got a camera that camcorder. Now this camcorder, let me show you something really cool about this camcorder. I've got a remote here. This remote has an LED on the end of it that you can't see normally. If you push on a remote and look at it, that doesn't light up at all because it's in infrared. But some cameras can detect infrared. So if I if I point this at the camera, let's see if I can get that in there, and I push a button, you see that light up? When I'm looking at that, I can't see it light up. Let me see if my webcam will do that. Oh, see that the webcam can barely detect that. See that? And it's showing it as red because it's in color. But this camera here, those old camcorders and stuff are really good at picking up ultraviolet. So what I want to try to do, and I'm not sure if this is going to work, I'm going to stick a wire in here. Well, I got to plug this in here. Otherwise it's not going to work. Alright. I got that plugged in. And let me take I've got a multimeter. I'm going to measure the, okay, I got it set to AC. So I think I can stick this in there. I think I can make contact here. There it is. So at the very bottom, the thing is I need 3 hands here to do this. But, so at the very lowest setting here, I could do it that way. So as I crank this up, you see, does the voltage go up? Yeah, it goes up. 15, goes up to about 18 volts. But on the lowest end, it's a volt and a half. So a volt and a half should not cause the wire to glow. And what I'm doing is I'm taking a wire here, just an ordinary, multi-filament or stranded wire. Can you see that? And there, I'll do it on this one. And this is a stranded wire, and I'm taking one of the strands of the wire. So it's a very, very thin wire. I didn't measure it, but how thin it is, but it's probably about, I don't know, maybe 20 or 30 microns or something. It's really thin. About the width of a hair, I guess. Yeah. So, but the remote controls are infrared. We got some chat here. Hang on just a second. Good way to zap yourself. Yeah. 18 volts shouldn't hurt me. I don't think that's going to hurt me unless I do. You have to get some impedance and stuff in there to zap yourself with that low of a voltage. So I'm good in terms of the voltage. Now in terms of the heating this thing up, I've burned myself with a wire like this before, a thicker wire. I had a thick wire and I shorted it out on a lithium-ion battery, and the thing glowed really hot before it melted. And I happened to have my thumb on there, and it just sliced right into my thumb. And man, it really gave me an injury. So yeah, don't try this at home, kids. This is not. Yeah, you gotta know what you're doing. Sometimes I know what I'm doing, but we'll find out if I do now. I tried that when I first tried to figure out this experiment. I tried to do it with a 9-volt battery. It should work with a 9-volt battery. 9-volt battery should have enough current to, if you lay a thin wire like this across it, to melt it. But for some reason, I don't know, these batteries are old or whatever it is, and I measured them. It's more than 9 volts. But when I put that wire across there, there's not enough current from this old 9-volt battery. I think you can do it with a 9-volt battery. I just don't have the fresh batteries. And what else am I going to do? Oh, I'm going to get, before I do any further, I'm going to get some safety glasses, because I don't want little bits of metal coming into my eye. And also, it's going to glow for a fraction of a second. It's going to emit ultraviolet light because it's going to get really, really hot. So I'm going to get safety glasses that filter out ultraviolet light and protect my eyes. So let me run and get that just a second. I'll be back. Okay, couldn't find my safety glasses, but I found this cheap pair of glasses that I bought at the dollar store. These are plastic, acrylic. They filter out ultraviolet. These I know filter out ultraviolet, but some glasses. I bought one pair of glasses once at a dollar store. You know, just like reading glasses with plastic lenses. And I was experimenting with it, and one of the lenses filtered UV and one of them didn't. From the same pair of glasses. Kind of weird. And these will protect against anything that flies out of here. It'll protect my eyes. It might mess up the glasses, but... And this is, because this wire is so thin, even though we're going to get it really, really hot, it cools off very quickly because it's so thin. And because it's so thin, the ratio of the surface area to the volume at any particular length of the wire is large when it's really small like this. When you get the thicker the wire, because the volume of the wire is the way you figure it out. It's, what is it? Pi r squared is the surface, and so anyway, the thicker the wire, the smaller the ratio of the surface area to the volume of the material. That's why, you know, these, when they store liquefied natural gas, they use these huge tanks. That's because the surface area of the tank is small compared to the volume. So on a thin wire, surface area is a lot larger, which means there's more surface for the heat to dissipate, and so it's not going to stay hot very long at all. If that makes any sense. So it's not like you have to worry about it, you know, falling somewhere and catching fire or something. By the time it hits the ground, if it just happened to fall out of here, by the time it hit the ground, it would be cool. That's how quickly it cools off, even when it gets really, really hot. I don't know if that makes any sense. But all right, so we're going to try this here. I wonder if I can. Let me. This will be even more dramatic, I think, if I shut this light off. I still got enough light here. I can see. Now, is that showing up? Can you see that still? Maybe I should just point. Let me do that. No, that won't work. Well, I'm gonna try this. I think you can see it there. Yeah, you can make that out a little bit, I think. These are the terminals. So I'm sticking them between, turn that down. And I'm gonna, I think I got a pair of pliers here somewhere. Well, I gotta turn it, I'll just do it. It's okay, I don't think I'm gonna burn myself here. Oh shit, I gotta turn the light on to see what I'm doing there. There we go. Okay, so I got that little wire in there. Let's see. I've got one piece of it going to the ground, another one going to this terminal here, which is controlled by that variable it's not a variable transformer, but it's kind of like that. So when I crank it up, it should make more volts, which means more voltage means more current, because we have a set, at least at the low temperatures, we have a set amount of resistance. So it's going to be more current, and more current means more electrons flowing, which is going to heat it up. So here we go. Now, all right, I'll just try it and we'll see what happens. I'll turn up just a little bit here. I'll do it as slowly as I can. Oops, there it goes. Did you see it? So that's experiment we just did there, was the experiment that this guy did, Ebenezer Kurzweil, on 1768. Now he used probably a chemical cell to get the electricity. Of course, he didn't plug it into mains. In 1700, they didn't have mains electricity and all that. So what we did is I turned it up, and I didn't get very high. I got it up to about, let me measure how many volts that is. It wasn't very many volts at all. AC. And I don't know. I don't have a current meter. Unfortunately, this current meter. So that was about 5 volts or something, 4 or 5 volts. And the current of this particular transformer is maxed out at about 2 amps, but it doesn't take very much at all when that wire is really thin like that. And so what happened is it heated up, and now the resistance of copper is supposed to go down when it heats up. But that didn't affect it. It didn't affect the current, enough to keep it from completely frying like that. So if we did this same experiment in a vacuum, it wouldn't burn up. It would melt eventually. But they later on went to use carbon and as I said, platinum. And then they took platinum and did some things to it to treat it in a way that it got coated with carbon. And anyway, the whole filament thing. There's one of Edison's helpers. Let's see if they have that in here. Wrote a book on electric light filaments, and he was like the main guy who really helped invent the stuff for carbon filament and vacuum. I don't know if they have him in here. Most of them. But it was a black man who actually wrote the book. He literally wrote the book on carbon filaments for the light bulb, and he worked for Edison. And Edison got all the credit. Look at it. I don't even think they have it in here. Let's see. I forget his name, unfortunately, because they don't talk about him very much. But he was the guy who actually did it. Probably because he was black and there was prejudice back then. 20s, it was pretty bad. There he is, Lewis Howard Latimer. This guy. Oh shit! I'm sorry. I don't have the. There we go. This guy, Lewis Latimer, employed at the time by Edison, developed an improved method of heat treating carbon filaments, which reduced breakage and allowed them to be molded into novel shapes, such as the characteristic M. Received a patent for a process of manufacturing carbons. Patented other improvements, such as a better way of attaching filaments to their wire supports. So yeah, this guy did all the work for Edison, But nobody talks about this guy. I couldn't even remember his name because they don't talk. People don't mention him, but he's the one who really did the work, and he wrote a book about it and everything. Lewis Howard Latimer. So basically, this is the experiment I did today was like the first step, and they did more and more and more. They put it in a vacuum. They experimented with different filaments and all that. And one of the key things was this guy's work on filaments. that made it commercially viable. So that's kind of cool. Now there's another experiment that I could do using a pencil lead, which I'm not going to do. But you can take a thin, these mechanical pencils that have the really thin pencil lead. I don't know if they still make these anymore, or poof. Oh yeah, I forgot to look at my chat here. Let me catch on chat here before I go any further. Good way to zap yourself. Yeah. Oh yeah. They all seem to these days. Yeah, it looks blue, but the remote controls are infrared. Yep. Yeah, they're all infrared. Copper wire not resistant enough, I guess. Yeah, it's when it's the thinner the wire, the more resistance, and the longer the length, the more resistance. But when it's a long length, then the heat created by that resistance is distributed on a longer length, and so it doesn't burn. But if you shrink the diameter and make it really, really small, like we did, taking just a tiny filament, one of the filaments of the strand, one of the strands of the copper wire, then it's thin enough to do exactly what we showed there. Maximizing the area of glowing thing with all those cold coils. Yeah. Poof. Yeah. Right. So we're. Oh yeah. So if you take one of those mechanical pencils, I don't know if you're familiar with those. They probably don't make them anymore, but they had mechanical pencils that had little teeny thin leads in them. That the pencil, you click it and it would extend the lead. The idea is you don't have to sharpen the pencil. You're right with it, and when it gets too long, you click it, and it makes more of the lead, the pencil lead. And it's the lead of the pencil, of course, is not lead, L-E-A-D, lead, the element lead. It's made out of it's carbon. So, but if you take those and you put electricity on one of those, the same thing. It conducts the electricity, but the carbon glows a lot hotter, and you get a really intense pulse of ultraviolet light from a lead, from a pencil like that. Anyway, that's what these guys did. Is they started with this thing, just taking a thin piece of wire, hooking it up to a chemical battery, and watching it go poof, and saying, "Oh, look at that! If we could keep that light going, we keep that thing going, it would make light. We wouldn't have to burn." Have candles or whatever, to make light. And it took them a couple hundred years, I guess. When was this? What did I say? 1780. So they started in 17. That experiment that I just did was they did it first in 1761. And so it took them almost 150 years before they got it commercialized, where they could actually use it. Sell lights with it. And then we went another over 100 years, right? This one, Edison did his in. Let's see. So it was a little bit less than 150 years. A little over 100 years. But then it took over 100 years after that before we got the LED lights, and fluorescent lights came a lot earlier. And then they had arc lamps, which is taking two pieces of wire close to each other with certain gases in there, and enough electricity, it will cause a spark to go between the two wires, and that makes a light. But that wasn't practical because it took a lot of electricity and it made a lot of light, and a lot of it was UV, and so it was only good for lighting big, large areas. And they used arc lamps for a long time, like stage lighting and stuff like that. And also it made a lot of spurious electromagnetic radiation that interfered with radio transmissions. That was another problem with arc lights. But yeah, it took them a long time to get from that, the first experiment that we did, then to incandescent light, and then fluorescent. I forget when fluorescent lights were invented, but fluorescent lights is basically an arc. It's electricity flowing through a gas that gets ionized, almost like lightning, except instead of going through air, it goes through a neon or whatever usually a noble gas or a mixture of noble gases that cause the gases to ionize, and then the electricity can flow through it and make a light. And that light that makes is a really hot light too. It's ultraviolet. I'm talking about fluorescent now. Fluorescent tube. It's filled with a gas. Put two terminals on it, and then they also have to heat it up with a little filament to get it started. And then use a ballast, because once it becomes conductive, then the resistance goes way down, and the thing would short up and blow up if they didn't have a ballast in it. So they're going to have a ballast. But the electricity flows through that gas, and it makes a UV, ultraviolet light, that is not visible to us. But that's how, like a black light, you ever see the black lights? That's basically a fluorescent tube without just the raw UV light coming out of it. So what they do is they put a phosphor coating on the inside of the fluorescent light, so that the ultraviolet light, when the ultraviolet light hits the phosphorus, remember that guy that was talking about the electron jumping up and going back down and all that? What a phosphorus does is it takes a higher frequency light or a shorter wavelength light, and when it hits the phosphor, it causes the electron to go up, and when the electron falls down, it emits a lower energy light or a longer wavelength light that is in the visible range, and that's how fluorescent works, so that we can see it. And in LEDs, which is a totally different phenomenon altogether. But yeah, that's all has to do with blackbody radiation. It all goes back to blackbody radiation, at least the incandescent part of it. So that was my experiment. What else was I going to talk about? I learned about the other stuff, blackbody radiation. Okay, I've been on 3 hours. This is my longest stream so far. You guys want to talk about anything else? Anybody have any questions? Everybody fall asleep? Yeah. Oh, let me unplug this before I cause problems here. I need this plugged in. Let's shut this off. No questions. So we did an experiment. Made a wire go poof. Made a very bright light, which probably had UV component in it. I didn't catch anything on fire. I put this asbestos glove in here. I just wanted this is asbestos underneath the transformer, so it was pretty safe experiment. I wasn't doing anything that was gonna hurt anything or cause any problem. The worst that could happen is I could burn my finger, which didn't happen, so we're okay. Don't try this at home, kids. So blackbody, okay. Yeah, I think we covered it. Plancks constant. I figured out why the thing is curved like that, because the Plancks constant is not only for the determination of the quantization of the energy of a photon, it's also for figuring out the black body, which is Planck's black body law, which is a much more complicated formula. So that explained that. I think we got it all covered here. I could, we can look at fluorescent. I don't think I explained that very well. Let me look up fluorescent light, or we can explore more about Lewis Howard Latimer. Let's learn more about him, because people don't talk about him enough. All right, so he invented some other stuff. Massachusetts. Okay, that's right near where I'm in New Hampshire. I'm in the Upper Valley of New Hampshire, which is basically between New Hampshire and Vermont. The Connecticut River runs through there, and I'm right near there. I can actually walk to Vermont from my house here. So it's okay. He was in Massachusetts. All right, inventions and technical work. Okay, did some rail car work. Okay, draftsman, patent law, blah blah blah. They invented a modification process for making carbon filaments. Yeah, reduce breakages during the carbonization process. Yeah, so what he did is, remember I talked a little bit about the when they were taking a platinum, and they would carbonize the platinum, put carbon coating on the platinum, because carbon would is a really cool thing for making filaments. But it's weak, right? It breaks when it gets hot. So they put the carbon. They try to carbonize some other metal to make the filament, so it's strong enough to hold up to the heat and not fall apart. And it's but it's got this carbon part of it that glows really nice. And eventually they went to tungsten. So what this guy did, what Latimer did, Louis Latimer, he the process of making these filaments had a high failure rate because of the way they hooked them up and tried to carbonize them and stuff, and he figured out a way to reduce the breakage and increase the yield of the production of these filaments. And let's see, this modification consisted of placing filament blanks inside cardboard envelope during carbonization. Okay, so he took the filament, instead of just having the bare filament when they did the carbonization, he put it around cardboard, put a cardboard sleeve over the top of it so that it would give it strength during that process, so that you get a higher yield. So that's pretty clever. While in England, on behalf of the Maxim Light Company, he taught the entire process for making Maxim lights, including glass blowing, in 9 months to get the factory up and running. So he was very good at getting the manufacturing side working for making light bulbs. 84, he was invited to work with Edison. Okay, so so he did all that stuff even before he joined Edison. He was doing all this stuff. So Edison really hired him to get his expertise. Edison, along with the work he did with Edison, he also responsible for translating data into German and French. Damn, as well as gathering that information. Latimer also developed a forerunner to the air conditioner called apparatus for cooling and disinfecting. Pursued a patent on safety elevator that prevented the riders from falling out and into the shaft. Okay, 1924, because this is much, much later, after the Board of Patent dissolved, after the Board of Patent Control dissolved, Latimer went to work with Hammer and Schwartz until he retired. Okay. So yeah, guy did a lot of stuff, invented a lot of things, but nobody talks about it. Everybody talks about Edison because he was wealthy, right? That's why they talk about him, basically, you know. I guess they're the people with the money write the history, right? You know. And this black guy got left out completely, and nobody ever talks about him. Louis Howard Latimer. When the company was okay, so here's all his patents, all the patents that he had. Okay, technical book, incandescent light, electric lighting. See, he literally wrote the book on lighting, electric bulbs. Played the violin, flute. Early advocate of civil rights. In 1895, Lewis wrote a statement in connection with the National Conference of Colored Men about equality, security, and opportunity. Cool. In later life, even though Latimer is no longer active military, he remained patriotic. Veterans organization, all that. Okay. So, legacy. Let's see what they say about his legacy, because most people never heard of him. Anybody in chat ever heard of this guy? They don't talk about him very much. Let's see, 20. Okay. Okay. National Inventors Hall of Fame for his work that we were just talking about. Latimer Gardens. Okay, so gravestone, yeah. Cool. All right, now let's look up the fluorescent light just to see really quickly. Fluorescent light is less about the about black body radiation, but that other guy talked about it. Okay, I don't know how to spell fluorescence. Fluorescence. That's not how you do it, but no. See if they got a link at the bottom. List of light sources. Oh my goodness, look at this. Let me search it here. How can that not? Lamps, other incandescent bulb, nuclear high energy, astronomical luminescence, bioluminescence. Luminescence, electrodistant arc lamp, we talked about that. There it is. Oh, FLUOR, okay, fluorescent lamp. Okay. Let's see if they have principle of operation. There we go. Fundamental mechanism for the conversion of electric energy into light is the emission of a photon when an electron in a mercury atom, okay, it's mercury that's doing it, okay, atom falls from an excited state to a lower energy state. Electrons flowing in the arc collide with the mercury atoms. Okay. If the incident electron has enough kinetic energy, it transfers energy to the atom's outer electron, causing the electron to temporarily jump to a higher energy level that is not stable. The atom will emit an ultraviolet, that's what it's talking about, ultraviolet photon, as the atom's electron reverts to a lower, more stable energy level. Most of the photons that are released from the mercury atoms have wavelengths in the ultraviolet region of the spectrum, predominantly wavelengths 253.7 and 185. Okay, yeah, that's right, it's a mercury. There's other gases in there, but maybe those other gases are just there to provide a conductor once they get ionized to cause the electricity to flow through. But yet there's a small amount of mercury vapor inside there. I remember that now. And so the Yeah, the wavelengths at 253.7 would be a black light. Like if you bought a black light, at a store or something, those are typically about that, or 265, something like that. And then these special lights that you can get for disinfecting, that actually produce ionizing radiation are at 185 nanometers. The shorter wavelength. That's UVC. That's the really heavy stuff that can, when it hits the little microbes, the bacteria or whatever, it ionizes their atoms in the molecules and disrupts their DNA and their structure so that it kills them at 185 nanometers. Okay, these are not visible to human eyes, so ultraviolet energy is converted to visible light by the fluorescence of the inner phosphor coating. The difference in energy level between the absorbed ultraviolet photon and emitted visible light photon heats the phosphor coating. Okay. So it heats it up a little bit, but not as much as an incandescent light. Right? Fluorescent lights are much cooler operating, which means they're more efficient, right? That's why they were so cool. That's one of the reasons why they went to them, because fluorescent light is much more efficient than an incandescent light. Most of the energy that comes off of the glowing filament of an incandescent lamp is in ultraviolet or lower heat and radio waves and stuff, which is why they're much less efficient, because most of the energy gets released as heat instead of as visible light. But fluorescents are more efficient because they start in the ultraviolet. All right, it's not heat. It's ultraviolet length way up there, and it hits the fluorescent, the coating, the phosphor coating on the inside of the fluorescent tube, which causes the electron to go up and go back down. What goes back down, it releases energy at a lower wavelength, and the difference makes a little bit of heat, but nothing close to what an incandescent does. So, which means that it's more of the energy is released as light, so they're more efficient. Electric current flows through the tube in a low pressure arc discharge. Electric current flows through the tube in a low pressure arc discharge. So yeah, the electricity is actually arcing through the tube. Let me read it here. Electrons collide with and ionize noble gas atoms inside the bulb surrounding the filament to form a plasma by the process of impact ionization. Okay. As a result of avalanche ionization, which means that it hits one, ionizes one atom, and then that splits and releases maybe more than one electron, and then they strike other atoms, and it's like a chain reaction, and spreads out, and you get this thing called avalanche ionization. The conductivity of the ionized gas rapidly rises, right? Because ionized gases are conductive by definition, right? Ionization means that the electron is free from the atom, and that's what makes something conductive. Metals are conductive because of their structure has free electrons kind of floating outside of the atoms because of the way they're bound together, which makes them conductive. And this is the same thing. So it's why lightning works, right? You think about it, how the heck can electricity flow, so much electricity flow all the way from a cloud all the way down to the ground? It's because it's ionizing air. It ionizes air, which frees the electrons to flow, which makes it conductive, and so it's just like a wire, and it flows down to the ground. or up to the cloud. Either way it goes. It's more complicated than that. I read some stuff about how lightning works, and they still don't understand it. It's pretty complex stuff. The conductivity of the ionized gas rapidly rises, right, allowing higher currents to flow through the lamp. Are they going to talk about the ballast? No. That's why they need ballast, because it's a kind of a runaway function there. The conductivity gets higher and gets more and allows a lot more electricity to flow through it. And if they just allowed that to happen just with two pieces of wire with nothing else, no other electronics or anything, it would become so conductive that high voltage would just fry everything out. So that you have a ballast that compensates for that. When the current gets high enough, it tunes it down and restricts it enough so that it just keeps going without running away like that. Let's see. The fill gas helps determine the electric characteristics of the lamp, but it does not give off light itself. And see, that's where I screwed up earlier. I thought it was the gas that was doing it, but it's not. It's the mercury in the gas. The gas is just there to ionize and provide a conductor for the electricity. Okay, the fill gas effectively increases the distance that electrons travel through the tube, which allows an electron a greater chance of interacting with the mercury atom. Yeah, so it's the mercury that's making the light. Additionally, argon atoms excited to a metastable state by the impact of an electron can impart energy to a mercury atom and ionize it. Okay, described as the Penning effect. This lowers the breakdown and operating voltage of the lamp compared to other possible fill gases such as krypton. Okay, so we kind of had it figured out there. We were close. I was pretty close, and then I forgot about the mercury, which was kind of the main thing. But I hear they're talking about germicidal lamps here. A germicidal lamp uses a low-pressure mercury vapor glow discharge identical to that in a fluorescent lamp. Yeah, it is a fluorescent lamp, but the uncoated fused quartz glass, the covering envelope, allows ultraviolet radiation to transmit. So it uses normal glass will stop ultraviolet. Sodium glass, like your windows are made out of, or whatever, just common glass, will filter out ultraviolet radiation. You need a special glass that allows ultraviolet radiation to flow through. And then there's another kind of glass called Wood's glass, which is the opposite. It lets ultraviolet radiation go through, but it blocks frequencies below ultraviolet. It's called Wood's glass. That's how they made. That's how they used to make ultraviolet lamps. Let me catch up on chat here. Let's see. Yeah, they all seem to these days. Yeah, it looks blue. Okay, and a copper wire is not resistant. Okay, yeah, I think I'm already caught up on chat. So, okay. So yeah, that's what they use. I bought some of those germicidal lamps at the thrift store, and maybe I'll do an experiment with that. I'll do an experiment. Take a day, take a stream, and do a bunch of experiments with UV radiation, and I'll show the differences between UVA and UVB and UVC, and how it reacts with different stuff. Yeah, that would be something to do. Those germicidal lamps are kind of dangerous. You don't want to look at them at all. And they're they're using them in hospitals now and stuff. And they can only sterilize the stuff that that the light actually reaches. So if it's under, if you got germs that are underneath in the shadow, basically in the shadow of the lamp. It's not going to kill those germs. So it's not really, it can help, I guess, but you still got to go through and clean the surfaces with some sort of disinfectant to kill all the germs. And they sell these germicidal lamps that you're supposed to, pass over your keyboards or pass over things to try to disinfect it. Got really popular at the beginning of the pandemic. Now people don't even realize the pandemic's still going. They don't even think about it anymore. So you can pick up these germicidal lamps very, very cheap, as I did at the thrift store. Let's see what else, if they have anything else there. You can see light emitting phosphors are applied as a paint-like coating inside of the tube. Organic solvents are allowed to evaporate. Tube is heated to nearly the melting point of glass. Wow. To drive off remaining organic compounds. Huh. Careful control of the grain size of the suspended phosphorus is necessary. Okay, so now they're getting into the weeds here and how they're produced and everything. Use kind of outer silicone coating applied by dipping a tube into the solution of water. Okay, ballast. Oh, here it is, the ballast. That's what I was talking about. Let's see if I got that right. I tried to explain how ballasts work or what the purpose of ballast. Let's see if I got that right. How much of that I did properly. Fluorescent lamps are negative differential resistance. Yeah, like I said, they get more. So as more current flows through them, the electrical resistance of the fluorescent lamp drops, allowing even more current to flow, right? It's a runaway process. Connected directly to a constant voltage power supply, a fluorescent lamp would rapidly self-destruct because the uncontrolled current flow. To prevent this, fluorescent lamps use a ballast to regulate the current flow through the lamp. Okay, I think I got that much right. The terminal voltage across an operating lamp varies depending on the arc current, tube diameter, blah blah blah. Okay. Typical T12 lamp is 430 milliamps with a 100 volt drop. High output lamps operate at 800 milliamps. Some operate at an amp and a half. Power level varies 33 to 82 watts per meter. Okay, they didn't really explain how the ballast works that I see here. Yeah, but I basically explained it correctly, I think. So, cool. I got something right tonight. Anyway. So. Alright. Well, that was pretty cool. This is one of my longest streams. I'm going to go ahead and raid out here. I'm going to try this new thing here. Raid Kim. I think I got that right. Appreciate you guys coming. Appreciate the raid. Appreciate you sticking through, and hopefully we learned something. Learned something new. I learned a lot of new stuff. Hopefully you guys learned some stuff. It wasn't too technical. All right. Invalid username. Okay, we'll try again here. There we go. Okay, raid created. Okay, let me play my closing here. Rolling credits. Appreciate everybody coming by. Hit the follow button if you think this kind of stuff is interesting. I also stream IRL and sci-fi movies and a whole bunch of stuff. You can look at it in my info there on my Twitch page. So appreciate you coming. Bye-bye. Stick with us through the raid if you can.
First thing we climb a tree, and maybe then we talk, or sit silently and listen to our thoughts. Illusion to someday, cast in a golden light. No dress rehearsal, this is our life. And that's where the hornet stung me, and I had a feverish dream with revenge and doubt. Tonight we smoke them out. You are ahead by a century. You are ahead by a century. You are ahead by a century.
Hi.
There in the morning shroud, and then the day began. I tilted your cloud, you tilted my hand. Rain falls in real time, rain fell through the night. No dress rehearsal, this is our life. Well, that's when the hornet stung me,